Good morning, ladies and gentlemen. Before I go into my little introduction, I'd like to introduce Professor David Sadler, the Provost of the University of Birmingham Dubai campus, to say a few words to us.
Thank you, Tariq, and good morning and welcome. And Tariq, welcome back to a campus that you've played a part in creating, of course, in your former role with the University of Birmingham. It's good to see you back here. As Tariq says, my name is David Sadler. I'm the Provost of the campus for the University of Birmingham Dubai. A few words of welcome from me and a few words of introduction to the campus so you know where you are, I suppose. We've been a fully fledged part of the landscape in Dubai now for 5.5 years. We started our first cohort of students in 2018. We moved to this building 18 months ago, and we were very fortunate it was opened by His Highness Sheikh Hamdan, the Grand Prince of Dubai, in April of last year, in a stunning ceremony, frankly, of long lasting in the memory. And we tried to do a number of things in this campus. So we do a very broad range of subject areas, first and foremost. Birmingham is a very broad university. It's a big UK university. There's a range of subject areas. We've brought a very broad range of program activity to Dubai. So we're teaching 56 different programs, for example, in this current year. We've gone very large on program range very early. And of course, there's a reason for that. We think that learning from each other across different disciplines is so important, and dialogue and communication is so important. So we want our staff to benefit from that interaction across different subject areas. And Birmingham, of course, is a very historic civic university. So old university, founded in 1900, a university of the city of Birmingham. And we brought that same kind of mission, if you like, to what we do in Dubai. So, of course, today you'll see a number of events going on. I was saying to Tariq earlier, it's probably the most complex set of events we've held at any one point in time. We're using different parts of the campus for different events today. It's towards the end of our teaching term, there's very few students around, but the likely is that you'll find other events taking place to interact with in the course of the day as well. And that's part of our contribution, particularly in this week, to the activity around COP28. So we launched a report of the university's contribution to the debate around mitigation on campus here last week. We've had a presence in the education hub at the Expo City site in the last few days as part of a contribution to the education for sustainability emphasis of COP28. And I will say that our students are passionate about sustainability. We teach one module called Enterprise, Innovation and Sustainability as a core part of the first year programme. And we block teach it next week. And it's absolutely a highlight of many students' first year activity. They come away just buzzing with ideas around entrepreneurship, innovation, sustainability. So our students really have, actually, I expect, a passion for environmental issues, and we try and sustain that passion in what we do. So enough for me. It's a very warm welcome. I hope you have a productive day with us. I'll be around most of the day. I have an engagement down at Expo City later on this afternoon. I'll be around most of the day. And thank you for being here.
Thank you, David. Thank you for that warm welcome. So, ladies and gentlemen, let me introduce myself. I'm Professor Tariq Ali. I'm the Pro-Vice-Chancellor for Global Engagement and Partnerships at the University of Liverpool in UK. And it's my pleasure to welcome you all on behalf of the Institute of Physics to what promises to be a most interesting, fascinating, complex, chewy, knotty set of discussions around climate change in the midst of all the activity going on in COP28 around us. Let me say a few words about the Institute of Physics. It's a professional body and a learned society with the main headquarters in London near King's Cross. And if you're ever passing by, do drop in and have a look. There's some great exhibitions going on, and it's a fabulous building. But there's also national headquarters in Scotland and in Ireland as well. It's a society for the UK and Ireland. You may have come across one of the many hundreds of journals published by the wholly owned subsidiary, the Institute of Physics Publishing, which has pioneered open access across the world and actually has footprint in many, many countries around the world. It's a very successful operation. The proceedings from today will also be featured in the magazine Physics World, which is widely read by physicists and non-physicists, again, around the world. So just to note or what you might say. It'll be picked up and reported all around the world. So the membership is about 21,000 members. And they pop up in many and varied roles, ranging from within schools, universities, national research facilities, to businesses of all sizes in finance, politics, and of course also in the arts. In the UK, there are more than 2.7 million people who work in industries powered by physics, and you can guess what they are, such as energy, healthcare, telecommunications, manufacturing, transport, aerospace, and so on. And so I think we felt it was right that to reflect the widespread role of physics, that we consider the challenges and issues around climate change from different perspectives, from academic, economic, business, and policy. And our distinguished speakers today provide a spectrum of insights from across these sectors and others. So the program today begins with a session on the global energy mix, followed by one on societies and cities, after which we will have lunch. We then will have a keynote talk on the science behind the current climate emergency, followed by a panel on sustainable transport systems. We also have short talks introducing a major report from the Institute of Physics, which has just been launched, called Physics Powering the Green Economy. And I'm going to wave one around now. Here it is. If you get the chance, this is the executive summary, but you can download it from the website as well. It's a terrific report. And before I hand over to the chair of the first panel, I'd like to thank the University of Birmingham for hosting us in this magnificent campus. My fellow organising group members, Dr. Helen Rogers and Henry Preston, and from the IOP, Dominic Hurley and Elora McPhail. And of course, to our distinguished speakers, thank you very much for your time and for joining us. There is ample time for questions from you all, and we hope you will join in with your thoughts and challenges. So with that, it's my pleasure to hand over to the chair of the first panel, Dr. Charles Ogilvie, who is the Director of Strategy for COP26, is a business leader, is an artist, is a scientist, is a true Renaissance man. Charlie, over to you.
Thank you, Tarek. I suggest the panelists kind of muster for the first section, so please, folks, come on down. I'd also very much like to thank the Institute of Physics and the University of Birmingham for hosting us here. For those of you who haven't been to the campus, it's absolutely beautiful and has far fewer motorways than Birmingham proper, which is to be recommended. I'd also like to thank Tarek for, first of all, his slightly overblown introduction and for being invited me to host this panel today. Folks, why don't we take a seat? What we're going to do is I'm going to say a few words of introduction. We're going to introduce the panelists. Then we're going to hear a little bit more about the new Institute of Physics report focused on climate change, and then we'll go into the presentations proper. I'm really pleased to be here. So as Tarek says, I've been working in energy policy in UK government for the last 10, 15 years, most recently on COP26. Somewhere along the way, I did my PhD looking at outsider science. So I interviewed plenty of people who were absolutely convinced that, for example, that gravity is a myth. And some of the more advanced thinkers got so far as to accepting gravity, but felt that relativity was a myth. So the prevalence and passion with which people believe things that you or I might feel to be totally counterintuitive or simply wrong is extraordinary. And as I think, and I hope this conversation will come on to, the enormous impact that misinformation and those myths have on our ability to tackle these huge climate challenges is really very real. I'm enormously grateful to the panel for coming, sharing both their expertise, but I hope as well talking about some of these issues in terms of how they communicate both as policymakers and the public. So I will hand over now for the panel to introduce themselves.
Thank you very much. My name is Lourdes Vega. I am currently a professor in Khalifa University here in Abu Dhabi, where I lead the Research and Innovation Center on CO2 and hydrogen, which in short we call the RICH Center, not because we are rich in money yet, but because we are rich in knowledge. And I'm also the acting senior director of the Petroleum Institute. My background is in physics. I am a physicist by training. I did my bachelor, master, and PhD at the University of Sevilla in Spain in theoretical physics. Even though I did my PhD half in physics, half in chemical engineering. And what I have been doing my whole life is trying to apply physics to solve industrial problems. So my background is statistical mechanics, molecular thermodynamics. So what I tell my students is we use the molecular glasses to try to understand from how the molecules behave, how we can design, improve, and optimize materials and processes, always under the umbrella of sustainable processes and products. So we work on CO2 capture, hydrogen, sustainable fuels, water treatment, design of refrigerants, always with this idea of how physics can help us to move into technology and the world. And today we will see what we do today. Thank you very much for inviting me. It's a real pleasure to be with all of you today. Thank you. In addition, I do other things, but I can talk about this later.
Hi everybody, my name's Julian Prime. I'm the head of statistics at IRENA, the International Renewable Energy Agency based in Abu Dhabi. My background is in statistics. And I've been an energy statistician since 2003 when I worked in the Department of Trade and Industry in the United Kingdom Civil Service. I spent around 15 years doing energy statistics in the UK, and then I moved to the International Energy Agency in Paris, where I led on their annual energy data. And 3 months ago, I moved here to Abu Dhabi, to the United Arab Emirates, and to Abu Dhabi, and to lead the statistics team at IRENA. Statistical information is so important to be able to understand the physics, monitor the physics of the energy domain, the energy transition. And so I hope that by the end of today, we will all know a little bit more about the physics and the data for the energy transition. Thank you.
Hi, good morning all. I am Rajesh. I am from India, and I work in Nuclear Power Corporation of India Limited, and I am there in that company for the last 33 years. I am into designing and construction of nuclear power plants, and I have worked in different technologies of nuclear and different capacities of nuclear plant. I have worked in PHWRs, pressurized heavy water reactors we call, and of different capacities of 220 megawatt, 540 megawatt and 700 megawatt, and light water reactor of 1000 megawatt. So now because of this net zero, nuclear has gained momentum in fact, and many companies who had stopped nuclear earlier are again coming back with this new technology. So let us hope this nuclear renaissance works in a good fashion to combat the overall target of net zero. And coincidentally, last week I was there in UK, and in fact last Monday on 4th I was there in the University of Birmingham, interacting the senior professors over there, delivering the Homi Baba lecture over there. Anyway, let us have a good discussion. Thank you.
Thank you. And I'd like to invite Anne Crean to come and talk a little bit about the Physics Powering the Green Economy report.
Thank you, Charlie. Good morning, everybody. Delighted to be here and looking forward to, as you said, Charlie, to a fabulous conversation about physics and its role in the energy transition. I'm Anne Crean. I'm also a physicist, chartered physicist, a fellow of the Institute of Physics. And my role at the Institute of Physics is leading our work in science and innovation. I won't say that because Tarek, you did an absolutely wonderful presentation, kind of giving an introduction to the IOP. But I think the other bit that I can add to that is why we're actually here. You know, why is the Institute of Physics actually at COP28? Well, back in just before COP26, our members kind of came together in a week-long summit because they knew that physics was kind of paramount to actually addressing climate change, driving the kind of targets towards net zero, but also kind of has an important role in growing the economy, the green economy. And so therefore, what they wanted to do was come together to tell the story of the role of physics, and also so that story could be told to policymakers so that we could start to influence policy to support physics and enable it to kind of resolve the biggest global challenge that we face. The work that we've been doing this year has kind of built on top of that, and we've kind of carried out an impact project where it's been championed by our Vice President for Science and Innovation, Professor Martin Freer, who's the Director at the Birmingham Energy Institute. The work has been supported by Sir Alok Sharma, who of course was the president of COP26 and who has been a supporter for the IOP for at least 12 years. As he proudly says, he is a physicist by background, so he is a subject dear to his heart. And what we have carried out is this work over 12 months, and the culmination of that work is the report which we've launched in time for COP. But importantly, we're here today because we've done this work, but we also want to kind of build on that conversation and hear your views as experts on this subject. So this is the report. We launched it literally, I think, a week ago. We've got some QR codes, so if you actually want to download the full report, please scan the QR code. You'll get the full report. It's a very detailed report, so it goes into a lot of detail. But we've got an abridged version as well, so if you just want to skim the executive summary, you will understand what the narrative is behind that work. To support the project, we engaged the membership. As Tarek said, we've got a large membership in the UK and Ireland, but also internationally. Over 500 of the members actually helped us in this project, including 26 experts who are primarily fellows of the institute that were working in industry and also academia, who are kind of leading in this area. We, as part of the work, carried out a survey, and in that survey, not surprisingly, 83% of the members that responded said that we are not on track to deliver net zero targets. And what they were saying was that they were concerned about that and they wanted to do something about it. So they wanted the IOP essentially to kind of start to kind of culminate action where they could actually be more proactive in driving the agenda. What you can see on the chart here is some of the reasons that they thought were the reasons for why we weren't on track. And they include government policy, lack of investment in R&D, and also a skills shortage. So if we're actually going to be growing the green economy, there is a significant gap. When they were telling the story of physics' role in the green economy, this is essentially the diagram that kind of came about. So we're talking about climate change, talking about driving towards net zero, but importantly, kind of realising that energy transition, which is an opportunity for businesses to kind of create products and services and jobs. There are three kind of pillars to this work. Firstly, looking at physics and actually giving evidence on the role of physics in some of the kind of key technologies which are kind of revolutionising the energy system. The second column is about the role of business, and in particular we were looking at businesses in the UK and Ireland that were working in applications from energy generation, transport, buildings through to decarbonising industry. And then the third column of work that we carried out was looking at what the enablers are, because it's not just about the technology, there's culture, ethics, to support that as well. And the kind of 5 key areas that the members wanted to kind of focus in on was for a healthy green economy, you actually need to have a broad range of physics skills to enable that to happen. You need to ensure diversity and inclusion because we need everybody kind of working on this as a problem. So therefore diversity is important to kind of drive innovation. skills, as I've mentioned, are critical. There was also quite a lot of discussion round about a fair and equitable transition as we move, both at kind of a local, regional, national and international communities, so that nobody's being disadvantaged through that transition period. And then, of course, it all comes down to the money. We need innovative financing strategies to enable us to get there. And what you're seeing on top of, or underpinning all of that work, is IOP had, as part of our policy work, has recently launched a report which is called the R&D Blueprint. And so in order for the UK and Ireland, which is where our membership is mainly based, we need to ensure that for a thriving physics R&D ecosystem, that these four kind of components are needed. We need to have strong discovery, so we need to kind of have investment in fundamental science, fundamental physics. There needs to be the right kind of ecosystem and support measures in place to enable businesses to thrive. We need to kind of have a skills, talent, careers strategy to kind of realise that physics ecosystem, and there needs to be funding in infrastructure. So that essentially was pulling together what was quite a complex conversation when you start to kind of drill into what is the role of physics. So this is hopefully encapsulating the span that was covered. Just as an example, as part of the work in the first column where we talk about R&D, we look at R&D investments, but we're also not just looking at the past, we were looking at the future. So the members came together, looking across those 5 technology areas, looking at what the priorities were for R&D investment. And they plotted out for each of those technology areas, essentially kind of critical paths and the probability of those being implemented. So this is just, you're not supposed to really see the detail, but it's just to kind of give you a kind of indication as to what you will find in the report. You'll find in the report these advancement profiles, which are recommendations on where future R&D investment should go. Going back just to kind of provide a little bit of evidence on physics and the dependencies in the green economy, we looked at data coming out of UK's research investment portfolio. So UKRI is the body that has the research councils that are making investments in the UK, and they're investing about 2.24 billion over the last 10 years in the green economy. And the work that we did, which was unique data analysis, showed that 73% of that investment is actually core and strongly related to physics. And if you kind of go wider than core and strongly physics, that there's additional investment that is. But what that's showing you is very much a reliance on the green economy on physics R&D. The other thing that we looked at were business demographics. So we've got some lovely maps in the report which actually show you where all the companies are in UK and Ireland that are actually operating and delivering products and services into this market. And we calculated about 1,772 companies across the UK and Ireland that are working in this market. And if you look at their combined turnovers, it's a huge number, 750 billion. And I think those kind of figures just kind of reinforce, that we've started the revolution. The technology is coming into the market, but there's more opportunity to kind of build on. And I think that's something that we want to kind of be putting out there, that this is a good opportunity. This is actually something that can be inspiring local communities. There are career path opportunities and jobs. So hopefully what we're saying is that the green economy is there and it's thriving and it's growing. And what we want to do is inspire next generation to kind of take advantage of that. So this is the final slide, summarising, unsurprisingly, physics innovation and physicists are vital to scaling up a sustainable global green economy, and vital to also ensuring that that is sustainable and has a just and fair transition. We're calling for a broad range of investment strategies for physics R&D, business innovation, infrastructure, and also for skills in this area. So we're working very closely with government departments, particularly in the UK and Ireland, to kind of ensure that the policymakers understand this and it's been brought into their strategies. We're also looking for that to be a long-term approach. So we want to see sustained investment for the next decade, so that we kind of drive this agenda. And we're going to want to be kind of putting forward the message that the physics community wants to be working with government in order to come up with strategies that will enable us to accelerate that transition. So essentially, what we're saying is that the physics community is ready to lend its weight and knowledge to drive that change. And certainly the physics community thinks now is the time for action. I'll just leave you with the last slide, which was in the foreword. It's a kind of quote from the Right Honourable Sir Alex Sharma, who was COP26 President and previous Secretary of State for Business, Energy and Industrial Strategy in the UK. And I'll also leave the QR code up so that you can download the final report. Thank you.
Thank you very much, Anne. And for those of you who think you've just seen a summary of the report and you don't need to read it, I flicked through it last night, and not only is the analysis fantastic, there were some really compelling essays by leaders from the physics community at the back of the report, which brings some of these specifics to life, and I thoroughly recommend downloading it. I did pick one thing out looking through the report last night, which was about the role of physics in leading public opinion. I think given the conversation we're about to have, that's a really important point to land on. This isn't just about communicating physics to the public. This is about the fact that physicists and scientists in general are trusted messengers to the general public. It's not just about explaining the ins and outs and the role of physics in this transition. It's about explaining this transition to the public. And why is that so important? Well, I think, and let's take the North Star of this COP, keeping 1.5 alive for 2030. But between now and 2030, we by and large know and have matured the technologies that we'll need to close that gap. We have economic models that can deliver these technologies in most countries. And we have, not complete, but we have policy solutions and policy design that we know works in driving these solutions forward. The piece of the jigsaw that is blocking progress to the 2030 milestone is political, is in the political space. We do not have enough political will at country level to turn technologies, economics, and the science of climate change into accelerated deployment. And politics is all about people, and that's where messages and myths become really important. I was at a panel event in the Blue Zone a couple of days ago talking about offshore wind in North America. Now, communities, coastal communities and conservation communities in the US have been bombarded over the last 6 to 8 months with information about whale deaths. Offshore wind turbines in the US are killing X numbers of whales a year. This has created an enormous pushback, both at state and federal level, against offshore wind deployment. Until about a week ago, there was not a single offshore wind turbine installed in North America. Misinformation in this space is absolutely rife. It's shaping the politics, and that in turn is slowing down delivering on what we need to do for climate change. So myth busting is fun, but there's something at the heart of this which is incredibly important, in that public opinion and the way that people respond to the facts or fake facts that they're told will ultimately determine, I believe, our success over the next decade. So I want to keep that in mind as we go down into some of the detail and the work that our fantastic panelists are doing, and we'll come back to that later on in the Q&A. So I'm going to first introduce Julian, who's already introduced himself. I'd like to welcome him up to talk to us about his work at IRENA. Thank you.
Great. Thanks very much for the introduction, Charlie. So yes, I am Julian Prime from IRENA, and I'm here to describe a little bit about the importance of data to ensure that we do get to our 2030 and 2050 goals, and also about what the infrastructure changes are needed, and just really covering why physics is important and why statistical information is important if we are to meet our 2050 goals. So my organisation, IRENA, has produced the World Energy Transition Outlook. It's a publication we've done for a number of years, and this year we've split it into two volumes. We have kind of the econometric modelling version, which has all the information about where we are, where we can get to, what we need to do to get to 2050 goals, the 1.5 degree goal there, and focusing on the different technologies that we need to develop and to continue with to get there. So focusing on renewable energy, but also looking at hydrogen, CCUS, and other key technologies that some have been around for a while, but are coming more to the forefront over the past few years, and certainly will be in the future. The second volume, which was released just before COP, has a slightly different insight into it, and looking at some of the social and dimensions on the number of jobs that can be created, what some of the environmental impacts are, focusing on energy access for all. So the fact that in Africa so many people still do not have access to energy, to even have a single light in their household. So it's very important that whilst we're thinking of some of the bigger picture of kind of reducing energy consumption, reducing energy use, we also need to think about the people, the populations where energy is a luxury at the moment, and we need to ensure that if we are to meet our goals, that we do not disbenefit those who are currently struggling. Underpinning the World Energy Transition Outlooks are outputs from my team. So we publish information on renewable capacity statistics, renewable generation and kind of overall energy statistics, and also we look at off-grid data. Off-grid data is something which often is not captured because it's not easy to measure. If it's not connected to a grid, how's it going to be collected and collated? Well, my team are very busy preparing our latest edition of the off-grid renewable statistics, and that's going to be published by IRENA in the next couple of weeks. So looking at the energy transition, we've still got a fair way to go. IRENA has developed 24 indicators looking at a variety of different things that need to be done to get to where we want to be by both 2030 and 2050. I don't want to go into full detail here, but you'll see the little indicator progress dials there. Most of them are looking very sad and pointing to the left, meaning there's still a lot of work to do. We've got about 6 that we're kind of sort of on track, but ideally we want more in the blue zone if we are to ensure that we have got a sustainable way of getting to 1.5 degrees. So where are we at the moment? What's the current energy mix? Well, we've got here a chart showing in 2020 what the total final energy consumption of the world is, and it's measured in exajoules, so 10 to the power of 18 joules, 374 of them. To get to 2050, consumption will need to reduce, and the fuel mix will need to change. We'll need to change from having roughly 3/5 fossil fuel in the mix to just over 10%. We'll need more electricity. At the moment, 22% of the energy mix is electricity, of which just over a quarter are renewables. For 2050, we'll need over half of the energy mix being electricity, and 90% of that being renewables. We'll also have extra sources of energy, so more hydrogen, with 94% of the hydrogen being from renewable sources. Looking at electricity, the current state of affairs is that we have roughly a world demand of 27 petawatt hours, so 10 to the power of 12 kilowatt hours, of which 62% is from fossil fuel, 10% from nuclear, and 28% from renewables. If we are to get a 1.5 degree scenario for 2050, we recognise that electricity demand is going to grow, as I showed in my previous chart, and the proportion of renewables, 91%. Fossil fuels will still be there. They will still be in the mix, but it's highly likely that coal and oil generation will have been phased out, and the 5% will be natural gas focused, and nuclear will also appear in the final mix. So, what progress has been made recently? So this graph shows the red line is the percentage share of new energy capacity that has come from renewable sources. So at the moment, just over 80% of new capacity that came on board in 2022 was from renewable sources, up from 15% in 2002. And you can see that nearly 300 gigawatts of capacity was added in 2022 of renewable sources, compared to about 60 gigawatts for non-renewable sources. However, the deployment is focused on a small number of regions, and it's really important that we enhance and expand the deployment of renewable sources to those nations which are struggling to have any electricity access. So the latest stats that we have show that 7,800 terawatts of hours of electricity were generated from renewables in 2021. The majority of that is hydro. People tend to not think that hydro is still a sustainable technology because it's been around for many, many years. If you had a straw poll of saying, what are renewable technologies, people will tend to say wind and solar. They forget about hydro. They forget about bioenergy that has been around for many years. But you will see that the largest changes over the last years have been increases in generation from wind and solar. You'll see there that between 2020 and 2021, wind generation increased by over 15%, solar generation increased by over 22%. hydropower fell. That's due to mainly due to the drought in South America that has had a huge impact on the specific electricity generation mix down there, because if it doesn't rain, it's very difficult to get hydropower. Equally, of course, a lot of renewables are variable, and if the sun doesn't shine, it's difficult to get solar. If the wind doesn't blow, it's difficult to utilise wind energy. So that's why you still need to have a variety of technologies in the energy mix. Here, I mentioned previously about some of the regional issues. The table up here shows 9 regions and the amount of capacity and generation that there has been in. This is 2020 data. The generation here is 2021 data. One of the surprising things, if you're not really into the data, is which countries are the big drivers of renewable energy. If you think about China, most people think coal-fired power stations, high emissions, etc. Well, China actually has the world's largest renewable capacity. In fact, the capacity of renewables in China exceeds the entirety of renewables in Europe and in North America. And that's just in one country. And that isn't something that people tend to think about when you hear about China's energy mix. Yes, they do have an awful lot of coal there, but they are also really developing their renewable generation capacity. So in our energy transitions outlook, we had a look at some of the barriers to the deployment of renewable energy going forward. And very similar to the comments that Anne made, the barriers that we are finding are some of the infrastructure barriers, making sure that the governments and policies are in place to develop renewable infrastructure, and also the skills, making sure that colleagues who have previously been working in coal mines have a future and work in other areas of the energy domain. And these are some of the solutions that IRENA feel are needed to tackle the energy transition to get to a 1.5 degree pathway. I'll conclude there. Thank you very much for your attention. And if any of you are at a loose end on Sunday, I'm hosting an event on looking at data for the energy transition at the IRENA Pavilion in the Blue Zone. Thank you.
Thank you very much, Julian. And now if I could invite Professor Lourdes Vega, who will be speaking to us about carbon capture, amongst other things.
Thank you so much. Here. I need to come here because if I'm there, you don't see me. Thank you very much. That looks better now. Okay, thank you so much. So it's because it has the animation, otherwise it will be a disaster the way it comes. So we were here. Now I'm coming back to my talk. Okay, so what is the situation today with the greenhouse gases emissions? I have to put this slide because I always use this information as my starting point. So I have here Carlos, one of my students, so he will be expecting this. This is why I always update my presentation the night before I deliver the presentation. So I was starting working on this particular topic because I've been working on carbon for CO2 for 30 years, hydrogen for 25. But this, I started to work on this 16 years ago. I attended a conference on thermodynamic properties, thermophysical properties in Boulder. And the plenary talk was given by Susan Solomon, who was at that time coordinating the IPCC report. And she used many data for an hour and a half, showing us how the human activity had an impact on climate change. So we are not saying that the reason for the climate change will be the human activity, but there is a direct correlation, and she showed that to us. So there are many talks, many data that she showed. I always use this one because I can follow up with this. So if you want to update this, the link is here, and they update this data on the 5th of every month. So we'll see the data from the 5th of December now, okay? So this is one of the many data you have. This is only for 5 years, and you have here the CO2 concentration in ppms that is measured in the manual app. So what you have here in red is the monthly mean value, and in black the same, but after the correction for the seasonal cycle. Long time ago, when I started to follow this data. This is the data from yesterday. So this is the data from December 5th, and this is always related to the month before and compared to the month before. So you see that the trend is very similar. You see, though, that the data is very different, correct? Because in 2007, what we have is 385 parts per million. Now we have 422. Worse than that, as I say, I use this data for all my talks, and I give many. As of today, unfortunately, I never, ever saw this data going down, even with COVID, because the data is in the atmosphere, correct? So even if you don't emit, the data will last there. So worse than that, for example, the experts in climate change were talking about not reaching 410 ppms because it will have some impact in the future. So we reached that in this particular measurement in 2009. Actually, since then we have been above that. This is a particular place in the planet, okay? So it's not that this is global, but globally it's also above that value. Okay, so doctora, professora, this is 5 years, that's nothing. Okay, so this data now comes from 1,900 until now. And you can see the increase in the emission of these greenhouse gases coming essentially from the energy combustion and the industrial processes. So this is where we are today. Where are these emissions coming from? So essentially from power. That's why in the previous talk we talked about electrification a lot. So from power, which is coal, 29%, power, gas, 9%, oil, a little bit, transportation, 23%, industry, 23%, and then we have buildings and others. So that's why I like to say that we are a planet in search for sustainable, but also secure and affordable energy. We call this the energy trilemma. Okay, and this is talking about data. So these are what we have here for the energy transition and the greenhouse gases emissions. This is where we are. This is where we have to be. And these are the different scenarios. If we have no climate policies, with the policies that we have, with the new policies that we need to have, etc. So I cannot give a talk in the Institute of Physics without talking about one of the greatest physicists in history. So this is from Albert Einstein, it's not from me. Those who have the privilege to know have the duty to act. And that's why now that we know this, we need to see how we act, because it's a privilege, correct? I don't have to invent anything. This is data coming from the International Energy Agency. This is a beautiful report they published last year on the energy overview system. And what you have here is the different clean energy processes that can help us to move through this energy transition. So of course we have the ones we saw before: renewables, hydrogen, CCUS, electrification, bioenergy, collaborations, behavioral changes that appear in the report. I love it. You will see that I report this many times. Okay, so if I put the lights for the traffic, so if I put red, yellow, and green to see how this is going through 2030 as a milestone to see what we can arrive to 2050, get ready. We are doing very badly. This was already said. Very badly means very badly. So what can we do? Okay, so here is some data from that report. You don't have to go into the details, but all I want you to see is the trends on some of them. So for electrification, this is where we have to be in 2030. You see that the slope of the lines is completely different from where we are to where we have to be, correct? This is where we are in renewable. So we are growing a lot, and Julian showed that before, but we are far away from getting what we have to get. Which is very important that we see how modern bioenergy is going to help us with that, in addition to the other ones that we saw. What about hydrogen and CCUS? No good news either. So in hydrogen, we are far away. And even though hydrogen is contributing, but it's not contributing too much, but it's contributing. But we are far away from where we have to be. And what about CO2 capture, utilization, and storage? This was the first trend. This is the second trend. This is where we have to be to decarbonize the fossil fuels. This is the data from last week. So this is the new report from the Global GCC Institute, and we actually see that, yes, there is an increase, there is a sharp increase in CCUS projects coming. So the data from the previous slide could be changed, but still we have to go. Now I go to IRENA. So this is the report. I love this report. Now I have to update with the one from 2023, but I love this report. So in IRENA, they define the 6 technological avenues that we need for the energy transition. So we saw renewables. So the data is different because that's a report from the previous year, but you will see that in essence, what we need to reach net zero emissions will be renewable energy, energy efficiency, electrification, hydrogen, and CO2 capture. And this CO2 capture, utilization, and storage comes from fossil fuels and from bioenergy as well. So, of course, we need to take radical actions. You saw that before. We need the political will that was mentioned before, but we also need game changes in technology. That's why we are here now. So, energy efficiency is the first one, and we don't talk about it, but this is something that is clearly needed. If the energy is more efficient, we don't need to worry about the rest, because for more energy efficiency, you will produce more energy with less emissions. But this is something you will do anyway. So anytime you will build a plant, you will try to optimize that. Renewables, we already have this plot, similar plot from before. So we are doing well, because that's from the previous report, Julia. So we are doing well on building new energy, especially hydropower, as it was mentioned before. Bioenergy is growing, solar and geothermal. However, we have a problem with renewable energy, because we need to have the energy whenever is required, not whenever it is produced. So that's called energy security, and that means that the supply of electrical energy requires the production when it's required, and we need to be ready for that. And some of the renewable energy, like wind and photovoltaics, are irregular. I mean, the plot shows it, and it speaks by itself. So how do we solve this problem? Do we have an excess of renewable energy so that at least we have the ones that we need? No way. That's economically not viable, so there's no way we can do this. So can we store the excess of produced energy? How do we recover this energy which needed? And are renewable fully integrated into the grid? These are questions for later if you wish. Well, anyway, part of this comes with the energy storage. So, of course, you can have renewables when you have storage as well. And this is actually needed, because otherwise we cannot rely on renewable energies. So when we talk about energy, I told you I have been working on hydrogen for 25 years. What is hydrogen goes up, down, up, down. No, it's very important. Oh, yeah, we will do hydrogen. No, hydrogen not too expensive. No, we do hydrogen. No, hydrogen too expensive. So now we are in hydrogen on the top. And why we have now this hydrogen on the top? What does it change? That hydrogen is not seen only for transportation. It's seen as a way of storing energy that can be used later to produce energy. And that you have that here. Hydrogen has the beauty of storing a large capacity of hydrogen, and also in long times. That's where it fits. Then we can talk about other things that we will leave that for later. But this is part of it. Hydrogen is not only seen for transportation, it can also be seen as a way of storing energy. And actually, that's the role of hydrogen. So hydrogen will work for many things. This is one of the many value chain stories of hydrogen. You can produce hydrogen from renewable or from the grid. Then you can produce it from water, and then you can use it for industrial applications, power, many things. Anyway, producing hydrogen today is expensive. Producing green hydrogen is expensive. So then we go to that later. Let's talk about the value chain of hydrogen. I will have this for the pink for you later. So here we have the hydrogen production. I explained to myself, I give a course on hydrogen to senior students undergraduate. So I explained the different ways of producing hydrogen based essentially on two things: the molecule, where the hydrogen is coming from, and the energy that you use. And that will give you the colors of hydrogen, the whole rainbow that we have of colors. So the hydrogen is, most of the hydrogen is produced today is called gray hydrogen. So it's coming from natural gas, steam, methane reforming. So you need water and methane. You produce from any electricity, from the green, and then you have the hydrogen, and then you have the CO2 that you need. That's why it's called gray. Exactly the same process brings you blue hydrogen if you put the CO2 unit to capture the CO2 before it goes into the atmosphere. If you use natural gas and pyrolysis, you produce turquoise hydrogen. Doesn't emit CO2 into the hydrogen, it produces solid carbon. Then water and renewable energy will give you the green hydrogen and also oxygen. And if instead of renewable energy you use nuclear energy for the same process, then you produce pink hydrogen with oxygen. And then there are other ways. So by the way, the hydrogen is no color, correct? It's just because of this. Let's think that hydrogen has a color. But this is the first part of the value chain. Then you have the hydrogen transportation, that depending where you're going to send the hydrogen, you use different ways of sending the hydrogen. And then you have the hydrogen utilization, which will be the same ones for which we are using hydrogen right now. And we add some other applications, like producing heat and power, for example, for the mobility and for heat, as I mentioned before. Why I'm explaining this? Not all these technologies are low carbon. Of course, gray hydrogen is no low carbon. Not all of them are mature technologies, so we need to work on this, and physics is essential to develop this. And all of them are used at large scale, essentially because not all of them are mature technologies, correct? So there is room for all of us. So that's hydrogen. And now how is this related to CCUS? Well, because when we produce blue hydrogen, we need to use carbon capture to make this blue hydrogen, correct? Most of the hydrogen today is produced from gray. So in the energy transition, and this is part of the strategy of this country, we will first have blue and then blue and green together. I think you know where the CO2 is captured from. So the technologies for capturing the CO2, this is the mature technology that is used in industry today, is absorption by aqueous amines. But because it has some bottlenecks, like energy-intensive impurities and losses of solvents, we need to develop technologies to improve that. One of the technologies we are developing is actually solid adsorbents. You don't have the evaporation at that time. And again, physics come into play, because you need to see how the molecules interact with the materials, how to modify the materials to increase this capacity, and then you do the solution of the processes. This is part of the story. Once you capture the CO2, you need to condition the CO2, either for storage, permanent storage, enhanced oil recovery, or for the different applications. This is a book I wrote in 2010 about the applications of CO2. So how big are the opportunities for utilizing CO2? I give you the numbers and we talk later about it. Okay? So today we use 0.6% of the CO2 that we emit, which is very small. Okay, then how can technology help? Actually, technology can help, and physics can help to develop these technologies in the whole value chain of CCUS, from the capture, monitoring, transportation, cost reduction, etc. I explained this already to you because I had this slide about the REACH Center. This is my one slide about the REACH Center, but I explained this to you just to mention that in 4 years we have 200 publications, 12 patents. We had more than 200 presentations in conferences, and we raised up $10 million external and internal funding. I want to finish with this one because that will give the floor to the next one. So this is what I showed you before. Now I put here the where this energy is essentially coming from. So we talk essentially about replacing some of the non-renewable energies by renewable energies, or using CCUS to clean some of these technologies, or replacing hydrogen to help with the hard-to-abate sectors. But I want to give the floor for nuclear, which has also words to say here. So thank you very much. You want this also?
Yeah, this is good. I'll manage with this. Thank you for classifying nuclear as a clean energy, clean source. Rather, it's not a renewable, but obviously it can be classified as clean energy that you can tell. And maybe that pink color of hydrogen can become green or something in due course of time. Pink has to be made green upon time. Okay, fine. Yeah, thank you. No? Something else? Yeah.
The point is that if you saw in my plot, in none of them were nuclear, because that's what you have to put.
Fine. Thank you. Yeah. So I'm again repeating, I'm Rajesh. I'm the technical director of the company, Nuclear Power Corporation of India Limited, where I've been working for the last 33 years. And we are into establishing nuclear plants in India. It's not audible? Okay, fine. Sorry. Now, my previous speakers were, of course, relying on the data published by IEA and IRENA, but now I'm relying on the data published by IAEA, which is my business over International Atomic Energy Agency. So, this is the projection what they have given for an energy of 434 exajoules today to 535.1 exajoules in 2050. That means it will increase at an average annual rate of approximately 1%. Whereas electricity consumption as on today or 2022 it is hardly 20.1%, and by 2050 it has to reach around 30%. That means electricity growth will be around 2.4% per year. That is the projection, and rather electricity consumption is expected to almost double by 2050. That is the present projection given by IAEA. Now, if you see the world scenario, this is a bit disturbing, like in 2020 last year, coal and oil and natural gas, that alone is contributing to around, let us say, more than 50%, less than 60% of this total electricity produced. And nuclear is very less, obviously, and the total electricity produced by nuclear is 9.2%, and 20.1% of the final energy consumed was electricity. This was shown in the previous slide also. So this we are talking about controlling this coal, oil and natural gas, and how we can control this or bring down to zero and can be replaced with all other renewables and clean energies. Now, if you see the current status of nuclear plants, 412 reactors are there in operation world over, which is giving around 370 gigawatt. You can see that the earlier plants, were less than 1 gigawatt capacity. Smaller capacity plants were there. That is where the ratio is less. But now, 58 nuclear plants are under construction, and large number in China and India, and 60 gigawatt. That means large capacity plants are coming now. More than 1 gigawatt plants are, each unit capacity is more than 1 gigawatt. Like that, it is coming now. So this is the present projection. I mean, and this may get over in another 5-6 years from now. And this is the regional distribution of nuclear power capacity. If you see Asia Far East, and this light blue is the line where you have large under construction plants and in operation plant. In US, America and in Europe, this plants have been established way back and they have stabilized and they have stopped those construction. Whereas in Asia Far East and Asia, Middle East and South, where we also belong, like here large constructions of nuclear plants are happening. So in the developing countries, we can say in Asia, Far East and Asia, Middle East and South, lot of nuclear plants are getting added, and Europe and Northern America, the construction of the plants have stopped and very few are coming up. So the reason being, this technology has matured in those regions, and upon time, they stopped construction of nuclear because of some reason or the other, and now because of this net zero or something, again they are revamping back. So this is the biggest challenge now because of the availability of skilled manpower which are required in those countries, even though their projections are very ambitious. Now this is again an IAEA data. It is expect total electrical generation capacity, as I told earlier, will be increasing by 22% by 2030 and then double by 2050. Nuclear electrical generating capacity is projected to increase by about 24% only by 2030 and increase by 140% by 2050. So this is the projections what has been given, and there are some low and high projections given. Low means some of the plants which are there have to be retired, maybe the plant life around 30 to 40 years, and after that they have to be taken out of service. In India, we have summer program known as PLEX, Planned Life Extension Program, PLEX program we call. After 40 years or 30 or 40 years of service, what we do lot of in-service inspections in the plant, and after that we assess what our components has to be replaced or something like that, and we extend the plant life for furthermore 30 years. And the unit electricity cost of such a plant, in which plant life extension has been done, will be very cheap. Now coming to Indian scenario, as of now, it is hardly 7.3 gigawatt or something in 2023, and by 2032 it will be increasing multifold to the order of 22 gigawatt. That way we are increasing in India, and pan India we are constructing nuclear plants, and there are 23 reactors in operation totaling 7.4 gigawatt, and under construction we have total 7.5 gigawatt, and another 7 gigawatt plant will be operational by another 2032. So altogether put together it will be 22 gigawatt in another 7 years from now. It's not that India is progressing only in nuclear field. In 2930, this is the mix. What will be the energy mix in India? This is the scenario projected. So you can see solar and wind altogether, that will be 50% in India, and nuclear will be only hardly 2% at that point of time. And the total consumption or installed capacity is going to increase, but in hydro, small hydro, pump storage plants, solar, then wind, biomass, all these things put together will account to around 60% in India, and coal and gas, which is the present day target, will be around 35% in India. This is the projection in India by 2030. Now, one of the fear of the public, why nuclear power is required, why nuclear plant is required, because it is unsafe. This is one, all these things are subjective only. This is one objective chart of the data given from our nuclear plants in India at various sites. It emits radiation, that's what public fear is there. There is one natural radiation which comes out, which is there everywhere, and that is around 2400 microsievert per year. This is the value of natural radiation, and we have a regulator. It is Atomic Energy Regulatory Board. Every country have a regulator. So their limit is around 1000 microsievert per year. You can see from all our plants, these are different sites where our plants are located. It is in the range of maximum is 24, which is coming in one plant. Other than that, all are in zeros or digital, very small minuscule values. And another important factor is we have a strong independent regulatory mechanism, and no incident of release of radioactive beyond the stipulated limits in public domain for over 33 years. So, and another thing is public dose is insignificant fraction of AR limit and natural background. This is the crux of the story objectively, how you can say that nuclear power plants are safe. Now, how a nuclear power can help in energy mix in long term. This is one chart which has been given by IPCC in 2014. Whether it has got revised or what, I have no data. But life cycle emission, of different technologies available. Of coal, it is 820 gram CO2 per unit of electricity, whereas nuclear is coming comparably with wind. It is 11, wind is 11, and nuclear is 12, hydro is 24, and solar is in the range of 27 to 40s. And obviously, gas and coal are the leaders in emitting CO2. So nuclear as such, it is comparable with any other renewable projected over here. And another advantage of nuclear is, upon time, the capacity factor has increased in nuclear. You can see greater than 90% or greater than 40%, the capacity factor is very large. Capacity factor is something like, she was mentioning that solar or wind, which renewables are there. When wind is there, then only wind power will be there, and when sunlight is there, then only solar power is there. Whereas in our nuclear plant, or even comparable to coal plant also, 24/7 it keeps on running. That is one of the greatest advantage. So these are known as base load stations. Let us say 1 gigawatt plant is there. For 365 days, 24/7, it will be pumping in 1 gigawatt electricity to the grid. That is one of the greatest advantage with this clean source of energy. Another comparison I am putting here with respect to what is the area required for a hydel plant or nuclear plant or coal-fired plant, and how it can be compared. Like, for a 1000 megawatt or 1 gigawatt plant, for a hydel plant, there will be a submergence of around 2000 to 5000 hectares. And whereas for a nuclear plant, it is hardly 20 hectares, very small area only is required for a 1 gigawatt plant. And obviously for a coal flight plant, because of ash handling and other things, you require 70 hectares. And the plant load factor, of course, if monsoon is not there, where rains are less, or once you have continuous inflow of water, it is okay. Otherwise, average capacity factor of a hydel plant in our region, where we are fully dependent upon monsoon, it is hardly 30%. And here the capacity factor is of the order of 80%, and here also it will be 80% obviously. But the emissions are huge over here, and here there are no emissions, here also there are no emissions. So relatively you can see, with respect to a coal-fired plant, nuclear also is placing a good competition over here. Now, why in nuclear power? It is very stable. As I was telling, 1000 megawatt or 1 gigawatt plant continuously running, it will be stable. Then dense in the sense, the area required is less. Like here in Abu Dhabi or in UAE, they have established 1.4 gigawatt 4 units in Baraka. So from 4 units, you are getting around 8 gigawatt from a very small area, and it will be continuously operating. Then inclusion of nuclear power in the energy mix can help in lower the cost of reaching the target of net zero emission, that an approach based only on renewables. So renewable alone cannot help you in achieving the net zero target. Of course, advantages of nuclear power are many, like it is having a plant life factor, plant load factor, capacity factor also we call 80 to 85%. Another thing is, like the requirement of backing down during daytime when solar is available could be addressed by storing the output of nuclear energy during this time through a combination of dedicated pumped storage systems, or through delivering the nuclear energy during this period for desalination or for production of hydrogen. This is another thing which has to be explored into, and obviously hydrogen he has been talking, which will be used for transportation. Now different technologies, just I will touch upon. PSW, as we call, pressurized heavy water reactor, which our country, and next is light water reactors or pressurized water reactors. These are the two technologies where we have different capacities, and light waters are higher in capacity, 1000, 1200, 1400 and 1650, and these are proven, these are established all over the world. Now this is another one which is a hot cake nowadays. It is known as SMR, small modular reactors, which is less than 300 megawatt, but it's still evolving. It has not yet come out of the drawing board. But some of the key features, SMRs may come one day or other, maybe not in immediate, but it will be coming. The reactor core size of SMR is half the conventional PWR core size, and it is based on the principle, this is very important, it is based on the principle that it avoids hazards rather than controlling them. All other reactors, we control and mitigate the hazards, but here it is avoiding the hazards. Then the reactivity feedback coefficient remains negative. It is a part of physics, that number of neutrons, available for the sustained chain reaction, it is less than 1 here. And more of the SMRs use 5% slightly enriched fuel, but in fact some of them use 20% enriched fuel also. And another greatest advantage, like it's very less frequent refueling. Refueling length is of 3 to 6 years. Once you fuel it, then it can run continuously for 3 years without any disturbance. That's what it is being told. Like in our PSWRs, every day we refuel, and light water reactors average per year we have to refuel. Then we have in SMRs, they say it is fully passive. It is purely dependent upon natural principles of nature, and decay removal, it is depending on passive system. And another is significantly reduce emergency planning zone. Emergency planning zone is one which you have to have a watch around 10 kilometers or 15 kilometers, which is prescribed by the regulator. In case of something, like in Fukushima, they have to evacuate the whole radius of 15 kilometers. Now coming to SMRs, this is the status given by IAEA in 2020. If you see this, this circle, it's around 90%. And this 90% is still in early stage, you can say. Some are in early stage, we call conceptual design, basic design, advanced design, licensing phase. These are still in either in the mind of the people or in the drawing board or in thesis stage, and by the time this is implemented and coming to reality and put in service, whether it will be affordable and how fast it can be implemented, those two are the challenges in SMRs. Now, even though nuclear, I have been saying that everything is bright, there are some realities and some challenges in nuclear. One is obviously, large project cost and construction delays. This happens in nuclear, in a large capacity nuclear plants. There are some reasons because of that, like, there is a significant on-site work and civil construction work delays, and there is no standardization design. That is because of the seismic requirement of the nuclear plant design, where every place is unique for a nuclear plant design, and you have to slightly modify the design suiting to that particular place. So it will have you cannot fully standardize any nuclear plant. And another one is safety issues. Even though the operation has been, the progress has been excellent in this world over, except for few stray incidents, like core melt is one accident, which through safety analysis we cannot say it is zero, but it may happen. If at all it happens, then what will happen is core catcher has to be there, where the core melt has to be contained, and hydrogen will be produced, that has to be mitigated, then containment venting, then public fear will be against nuclear power. Then another thing is, as I was telling earlier, there is no emergency planning zone. That is something like, it is a very difficult thing to be satisfied through any sort of analysis what we do. And third one is this, another thing is like proliferation issues are there. So nuclear plant should be controlled always by a responsible government. It's not simply government, it's a responsible government who should own the nuclear power program, not by ownership, but it should have always a control of the nuclear power program, so that it doesn't fall in the what you call non-serious stakeholders. So how do SMRs address this emergency planning zone requirement is, they are doing some analysis and they are coming out with a trademark of no impact in public domain, and it is simply a walk-away safe reactor. Means you keep the reactor over here and all the public can walk around here. That is what the theory is going on now. But by the time it is put into place, it may be, my guess is it will be from 5 to 10 years from now. In India also we have one 220 megawatt smaller reactor, which we are pursuing as a SMR. It is a pressurized heavy water reactor, and this requires very small area of land only. Now, another why we are talking about net zero, but why such a situation has come, one reality is there, that 70-80% around the historical carbon emissions have come from these three blocks, like this United States, European Union, Japan, Russia, Eurasia and other countries. And these blocks, like China, India, Middle East and Africa, these blocks you can call it as developing countries, where they are trying to develop now and coming to the living standard at par with this. But they were not responsible for the earlier emissions what has been done, but now they have been constrained for achieving this net zero, which should not stop the development of these countries. Unless all of us work together, it will be impossible to achieve the net zero target. That's all. Thank you.
Thank you very much. And if I could invite our speakers to the panel, we'll do some Q&A. So if folks want to come down and take a seat. So I'm going to kick off with a few questions before opening it up to the floor. And thank you, first of all, to all of our speakers for their fascinating and detailed presentations. Julian, I'm going to start with you. So I was working in the UK government in 2010, and we submitted a forecast to the European Union for the UK's renewable energy mix in 2020. So we now have the benefit of hindsight. There was a 40 times difference between the amount of solar we forecast in 2010 and the amount of solar that was deployed in 2020. Now, spotting people's mistakes is always entertaining. But the consequences of that were, the UK did not start thinking about the impacts to the grid of all of this solar. It meant that we didn't start educating the public as to the importance of these technologies, and certainly that we didn't think about capturing more value in that sector in the UK. So these forecasts have a huge impact on the way that governments respond to technologies, build policy, and build politics. There's also the famous IEA curve, where they failed to forecast the explosive acceleration of renewable technologies every year. Are we not in a dangerous place where these models themselves are myths, and they inform investors and governments about a slower pace of change than what the real economy will deliver, and in doing so constrain that pace?
you're right. Models rely on good data sources, but they also require good brains to understand the technology, to understand where things are going to be going, to apply to the data that is already there. Give me a room of 100 people and ask them to say, where are things going to be in the next 5 years, in the next 10 years? They'll all come out with different answers. So it's, what logic is behind the model. And I think that if the logic is fully documented, is transparent, has got a lot of metadata behind it, then it's not always fantasy. It's open to good debate. And I think that is where, when you're looking at different scenarios, be there scenarios coming from IRENA or the IEA or the UK government or the IAEA, whoever, so long as the information is out there in the public domain on what is underpinning the scenarios, then people can think, this is something that can be done, it can be driven forward.
Thank you. And I should also congratulate IRENA. I think the work that you've done on tripling renewables has created a very credible pathway. And the campaign that you've done with the Global Renewable Alliance and others have really helped drive this agenda at COP. And if we see that text in the final COP outcome, I think it will be a huge credit to IRENA for the work that they've done.
I mean, over 120 countries have so far pledged that they will sign up for the tripling of renewables and the doubling of energy efficiency. So yes, it is good news.
So only 74 more to go. Thank you, Julian. Professor Lordes, we know that there have been attempts over the decades to commercialise CCUS technologies. I believe there is a large project in Australia which is yet to capture more than 10 or 15% of the CO2 from the exhaust gases. There will be plenty of people over in the green zone who will say that these carbon capture technologies, largely funded at R&D stage by the fossil fuel sector, are providing an excuse for scenarios to keep the production and development of fossil fuel going, when in fact we should be focusing on curtailing those fossil fuel production investments and focusing instead more wholeheartedly on a more renewables and potentially nuclear-led transition. Can you tackle that myth?
This is an excellent question. Can you hear me? This is really an excellent question, and you saw it's not from me, it's from IRENA, that we also need CCUS. If we don't have CCUS, it's impossible to decarbonize hard-to-abate sectors. And this is something we forget. So let's put it this way. If you are in the green zone, you think everything is green. I have heard people saying, very well-reputed scientists, saying, no more fossil fuels. This is the end of fossil fuels. We have to stop it today. And then you say, okay, how did you survive with the energy security that you need? And how did you survive with the sectors that are essential sectors for our economy? So there are different questions in your question. The first one is why the deployment of CCUS is slow. Well, you need to have first to believe that this is needed, to invest on this technology as a way to decarbonize the society, and this is part of what we call the energy transition. So we are not jumping from fossil fuels to renewable energy and nuclear overnight. That's why we have an energy transition. So we are going from fossil fuels to clean energy. And when we say clean, we don't say only renewable, we say clean, although renewable, of course, is where we are going in the end with things we have been talking about. So first, you need to believe that this is needed. So we need to change the speech on how this is happening. Second, where this is needed, where you really need to do this. If you can electrify, then you don't need fossil fuels, correct? But then you need to have clean electricity. And now, what do we do with the heavy transportation? Are you going to electrify an airplane? I don't think so. So how do you deal with the transportation for airplanes, for the ships, long distances, for heavy transportation in general. That's one. How do you deal with cement industry? Are we going to stop producing cement today? Because carbon is part of the matter that you need to produce your cement. So you need to find a way to decarbonize the cement industry, and this is by doing CCUS. If you help the CCUS with renewable energy, your carbon footprint will be still lower than just using the grid, correct? But you need to decarbonize that sector. And then we go to the third one, metallurgy. So how do we deal with the steel that we need and the aluminium? How many things do we have that are based on that? So do we have cars, do we have buildings, and many things that we need that. Again, the same. You need to use, this part of this is you can use hydrogen to reduce the carbon footprint of what we call the green steel factories, but you still need to capture the CO2 as well. And then you need to see what you do with this CO2 as well. So for sure we need, and by the way, also from bioenergy, correct? So depending on the bioenergy that you use, you will produce CO2. If you capture the CO2, you will have these negative emissions. But if you don't capture the CO2, you are emitting the CO2. So you need CCUS technologies, and that's recognized by the International Energy Agency, IRENA, and in any scenario as one of the key enabling technologies for the energy transition to decarbonize the society.
Thank you very much. And I've been very heartened at this COP on the focus of getting first-of-a-kind projects at scale on the ground. I know the Global Decarbonisation Alliance was launched last week, and the focus really on bringing investors, governments, regulators, policymakers together to say, if these technologies are an important part of these solutions, let's get some cement being poured and some chemical engineers on the ground screwing things together to find out what we can do and what the cost curves look like and what the efficiency curves look like. So I've been very heartened by the progress at COP.
This is essential, but that goes to the circle of you need to have first the push for doing this, then you need the financial help, and you need to have the technology ready, correct? And then once you have this, you can implement the technology. So they put it as a line. I think it's a circle, because if we don't have the technology ready, put all the money that you want, but we will be delayed. So we need to work together in all the fronts, and it's the COP. I heard actually that this is also the COP of CCUS. And I mentioned this in a panel discussion in COP 2 days ago. We need to believe on that to apply it.
The COP of CCUS.
That's what they say. I was shocked. I was shocked.
Shri,
I don't think so, but I was shocked.
Shri Veera Raghavan, I very much enjoyed your presentation. Thank you. In the UK, we have a particular experience of nuclear. As you know, we're building a new project at the moment at Hinkley Point. And the price agreed between government and the developer is around £92, so about $100 a megawatt hour. The conversation in the UK has always been the nuclear sector promising that costs will fall as we build out plants and us not seeing significant costs. And at the same time, the costs of processing the legacy waste growing every year. I think we spend about $4 billion a year in the UK just dismantling old nuclear reactors. Can you talk a bit more about cost reductions in the nuclear space? Because we were told that these large fission plants would come down in cost. And now we're being asked to invest in SMRs, which themselves are unproven, certainly as a multiple technology. Tell us what we can expect from cost curves, and reassure me that cost reductions in nuclear is not just a myth.
Okay. One of the first of all, thanks to you that you have not touched upon the safety of the nuclear power. I think you are convinced about the safety of nuclear power. Thank you. Only now cost is the issue. Okay. So we have our great visionary in India, Homi Bhabha, who was the father of nuclear power program. So he was mentioning no power is costlier than no power. Okay, that was the slogan. No power is costlier than no power. So cost should not be an issue, but it is really an issue as far as an investor is concerned, right? Because ultimately the consumer has to accept for this price, and he has to purchase that power. Now, what is happening in nuclear power in the developed countries? All these countries, UK, and Europe and US also, they proceeded with establishment of nuclear power plant very fast, and they stopped at some point of time. Okay, and there was a gap of 20 years, and now because of these reasons, it is coming back. So what has happened is all those skilled manpower, skills in the industry have totally lost, and they are learning and now implementing. Because of that, the cost is very high. And why it is high? Because they are learning and implementing, the delays are happening. And in any investment, when delay is there, that interest during construction or interest during that phase, it is very large. And that is the ultimate reason why a cost is high. Whereas in developing countries like China and India, where we are constructing a nuclear plant in 6 years average, 6 or 7 years, the cost is not that high because we have a huge industry base, we have huge skilled manpower, and the push from the government is always there for implementing this nuclear plant. Once we start implementing this very fast, the industry base will increase, and once the technology is developed and mature, definitely the cost will come down in due course of time.
Thank you very much. Yet another example of why long-term policy certainty creates cost reductions, efficiencies, mobilises capital at scale, develops skill bases. A theme which is covered off in this excellent report, I hasten to add. I'm going to ask you each to say a little bit about your role as, your public role as physicists and engineers, how you think that the work that you do could be, how you think the work that you do is effective in moving public opinion, and some of your experience of tackling myths. And I'm going to pass over to Tarek to take my role in moderating this session because unfortunately I'm out of time. So thank you all very much. Over to Tarek, and I will catch up on your answers when I watch this online.
Very good. Thank you.
Thank you.
So, over to you.
So he sends the question and he leaves.
He's every.
Okay, very good. So, well, I mean, I already used the sentence of Einstein. I think that's the one we have to use. No? So those who have the privilege to know have the duty to act. What can you do as an individual? Not very much. This is the truth. As an individual, no, because we need to work together. However, what we say has an impact. That's like the stone you throw to the water. You never know what you are saying, where it's going. I think we have to be role models for the new generations on telling them that the planet is in our hands. We have to do whatever we can do. So for my particular case, since I realized that as a physicist, I could help in this area, I have been working on this myself with the research and developing. When I was in industry, when I am in academia. That's what I try to infuse my students and collaborators. And anytime I have the opportunity to give a talk on this, I do it. And that's why, by the way, you can see me everywhere. So whatever we can do from the work that we do in the position that we have, whatever we can do when we talk to the public, whatever we can do when we talk to the media, publications that we do, etc. We have to bring the words that as physicists, we have a word to say to help in the energy transition and overall to take care of our planet. It doesn't have to be only energy. It can be water, it can be food. We have the opportunity to do this. We have the responsibility to work in this direction.
Thank you. That's a great answer. Let me, before we move on, so just in that respect, as you're going out and talking in particular to the public, have you noticed a difference in the attitudes around fossil fuels and carbon capture in particular, more previously? And then how does what you say as a physicist and the data and the underpinning science relay? What is the how does that come back in the dialogues that you have?
This is also an excellent question. So number one, as a physicist, I like data. So I always use data. And that helps people because otherwise you are talking about what? So you need to come with data. So I mentioned already that I wrote a book on large-scale uses of CO2 several years ago. So CO2 looks like dirty, correct? If you think about CO2, it's dirty. By the way, it's dirty. But then why? Because we have an excess of CO2 into the atmosphere. So if I start a speech drinking a Coca-Cola, and when I open it, I say, put the microphone here, that's CO2. So actually CO2 you can drink and eat. The problem is that we have an excess into the atmosphere. We need to see how we handle that. So then you can change the perspective of the people and you can actually act on what you are seeing right now. You cannot be patient. You have to be active. So I have seen this change in attitude.
Yeah.
Yes, I have. And okay, so we go again. I mean, you can use many different examples, no? Dr. Jekyll, Mr. Hyde. So you can use many different examples. CO2 can be good and bad depending on what you do. So for carbon capture, utilization, and storage, what we need to tell the people, and this is a reality, is that we need to use it for the energy transition. So you give data on, for example, how do you decarbonize steel, cement, etc., and that you use it because otherwise you don't have a house, you don't have a car. So we need to clean that, and people react to that. On the other hand, I'm talking about hydrogen, I have the opposite experience. Right now, hydrogen is here, so people think hydrogen will be the solution. No, sorry. Hydrogen is not going to be the solution. Hydrogen is part of the solution. So again, we have to explain that, because hydrogen will help in some sectors, but hydrogen is not the solution. You see countries, I don't know what to say any, because I am from one of them, in which we talk about hydrogen like that solution. So this is part of the problem. We can manipulate the public perception. We cannot manipulate the public perception. We don't have to give them data. If you can electrify, please electrify. If you can electrify with renewable, and if you have the right energy storage, do that. If you can help with the energy efficiency, that's the first one we have to do. So then talking about COP, so let's go into renewables, energy efficiency, and all the other things we have to do. We need to tell people that this is data, as I say. We have to tell the truth. We have to be transparent. Not because I work in hydrogen, hydrogen is the solution. No, it's not true. How can I say that? But can I work on hydrogen to make it cheaper? Yes. Can I work on hydrogen to make it more sustainable? Yes. Can I work on improving the efficiency of the processing which we use hydrogen? Yes. So that's what we have to tell people.
Thank you. Brilliant. Julian.
So I'm perhaps the only person in this room who isn't a physicist. I did get an A-level in physics, so which I'm very proud of. But then I moved into other sciences and to mathematics and statistics. But during my time working on energy data, I have had to get a grasp of the physics behind the technologies and the engineering concepts. And I've always been very impressed with how that has been explained and written and done in kind of plain English. And that's something that, from a data perspective, is also very important, because you may have heard of the phrase "lies, damn lies, and statistics." Yeah. That has always been the thing that, as a statistician, has been pointing at me. You know, is the information that you're putting in your publications that you're speaking about accurate? And as a statistician, I try to make it as accurate as possible by making sure we've got the best evidence and basing that on the engineering and the technologies behind that. So any fool can get some random numbers and add them up, but it takes an educated fool to make the real storyline behind it, and to be able to communicate that in a sensible way to the media and also to social media these days.
Yeah, thank you. Well, we love statisticians. I mean, please.
Yeah. I think I'm working in such a field which is the most powerful, or rather best invention of the physics, like nuclear. Nuclear has been the most powerful invention of discovery which physics has contributed, and I've been working in that. And neutron and radiation are the main things which I work upon, and I convey to the public. Public perception nuclear is always what you call ups and downs are always there. And objectively, we try to tell them that the means of radiation is by some unit of something, microsievert or something is there, and even though it's unfortunately invisible for them, like it's not coming out, no smoke is coming out from the nuclear plant, but some radiation is coming which they are not able to see. So we show them with the what you call instruments or radiation meters, by showing to them that there is a plant over there, and we all folks, thousands of fellows are working, qualified, educated fellows are working inside the nuclear plant continuously for years together, and we have no such issue, and you are staying way outside, and why the hell you want to worry about it? So this is how we are able to turn the public perception towards the nuclear plant. So physics is in a way the base of our nuclear core, that is, our reactor core.
But it was interesting what you said earlier in response to Charlie, in that you were pleased that the question he had posed to you was not about safety. To be, to some extent, I think the debate has moved on in the public discourse,
Yes.
and it's much more now about where does it fit in the global energy mix?
Yes.
How does it provide base load where needed? Can it be that pathway to hydrogen from thermal? Can it do desalination in those countries where it's needed? And fundamentally, is it affordable? So is that the best investment for your dollar? In the context, in the society, in the energy mix and the resources that you have in the country that you're operating in. So I think the debate to some extent has moved on in my experience, but I kind of...
That's a good sign, maybe this Fukushima accident somewhere in 2011 or 12, it changed the public perception slightly.
Yeah.
And there was a dip even in our country also. It had a slight slowdown at that point of time. We were constructing large number of reactors, and some safety review also was undertaken, all these reactors. It had what you call some 3 or 4 years impact in that. But unfortunately, Germans, they withdrew from nuclear. Totally, they shut down all these plants. They are taking probably nuclear energy from neighboring countries, and using them, but they don't have to have nuclear.
Yeah, no, it's hindsight, given what happened with Ukraine and the energy prices, they were probably wishing they hadn't done that so early.
Now let us hope that this nuclear will give a good solution for their total energy needs.
Yeah. Thank you, everybody. Let me just open it up if there's any pressing questions, because we have tea and coffee now. Has anybody got any questions? If not, please go ahead.
So, can I compare to
speak, because we're on camera.
I'll give you the mic to
Oh, even better.
and green. So, thank you for all those presentations so far. My question is kind of compared to where we thought we would be 10 years ago to where we are actually now. I know you mentioned about some surprise in the adoption of renewables. Is there anything else that's kind of really surprised you in terms of where our predictions have been completely off, especially with hydrogen and the thoughts around that and nuclear?
Who wants to go first?
Yeah, one thing I can say, the last 10 years, at least in nuclear, people have, like he was also mentioning, people have understood now safety is not the issue. How fast you can implement, that is the issue. So that way it is a positive change for nuclear as compared to last 10 years and today.
Let me jump in and just, so on the nuclear thing, the thing that surprised me most is the massive expansion of interest and the money and capital flowing into nuclear fusion. That and the companies that are being set up all of a sudden over the last 5 years, just in the last couple of days, John Kerry has just announced a big global collaboration and cooperation around nuclear fusion as well. I didn't expect that to happen, I must admit, 10 years ago.
Yeah.
Any other comments?
I mean, so certainly from a renewables perspective, it really needs the buy-in of governments to make sure that you can get where you want to be. In 2010, there was a lot of talk about where renewables would be in the future, but governments have really needed to put their money where their mouth is and invest in the infrastructure, change the mindsets to make sure that we can continue to develop and to get to where we really need to be, rather than where we thought we needed to be.
Final words.
Thank you. I'm going to talk about something different. Number one is we need to still solve the issue of transportation, which is one issue. And we didn't talk about two other things that are very important. One is the role of digitalization in all this scenario, and also the behavior of the people. That will move many other things. And in 10 years from now, you see that the new generations are much interested into clean planet, etc. How this matches with the comfortability that they also want to have, I don't know, because turn off the air conditioning and see what happens. But I put this example to my students because with Carlos we are working on renewable, on low global warming potential refrigerants, so that they don't have the impact with the environment. And then there is not a solution, by the way. We are working in this very heavily. But if you tell the students, no, this is high global warming potential, we are not going to have air conditioning. See what happens. So we need to combine what we have in theory in our mind with the behavior that we have. And the same applies for transportation, as I say. So I don't know if you're, I don't know how it's in English. I remember a series on TV that I was watching when I was little, the Super Fantastics. Now that they were all with all these flying in the air. Yes. So I don't know. We don't know what the future is going to give us, and I don't know if this is 10 years or what. But for sure, the technology has changed our life. Can you live now without a smart mobile? No. So maybe digitalization and all these things will also have a huge, much bigger impact into the energy mix and transition than what we see today.
Okay, thank you very much.
My smartphone is far smarter than I am. So on that
And now with artificial intelligence, now they write your papers, they write your report.
On that note, I think let's all go and have a cup of coffee upstairs. Thank you very much, everyone. Thank you to our speakers.
So, welcome back from the break. My name is Professor Nana Mabrown Kluchi. I'm currently the head of physics department at the University of Ghana. My research area is in atmospheric physics, and I relate a lot with a lot of the discussions that went on earlier in the earlier panel. I'm also a vice chair in the working group 1 of the IPCC for the 7th assessment cycle. Earlier on, I worked as a lead author in the 6th assessment cycle, which was published this year. Okay, so this is my email address for any further discussions beyond the room. I'll be talking on societies and cities and looking at it from a climate change perspective. Okay, so these are highlights from the IPCC assessment report. Just a few. This I picked from chapter 6 that focuses on cities, settlements, and key infrastructure. This is the working group 2 report. So in all cities around the world and urban areas, we have seen with high confidence that there's a risk faced by the people and assets from hazards that are associated with climate change. This it's published from a number of papers and a lot of evidence showing this. So this is reported with high confidence. There's also evidence that climate change is affecting people disproportionately, and like we said during the energy discussion, different people are affected differently also with climate change. And those who are economically low have low adaptive capacity, so they are kind of having more impact in that sense. Now, coastal cities also came up very prominently as going to have more vulnerable and having a lot of impact. I'll show a global map of the coastal impact as well. So these are a lot more of the impact we're having in the cities and the urban areas. Flooding, high temperatures, water insecurity, pollution, all linked with the issues of climate change. This is a map of the coastal cities at risk. And if I explain, the deeper the color, the higher, the earlier the risk that will happen to them. And then we have the percentage of the number of people that will be affected. That is in the circles. So the wider the circle, the more the people that will be affected. And the deeper the color, the earlier these risks are happening. So most coastal areas, if you can see from Asia region, Africa, Europe, America has few areas, South America. Madagascar is somewhere here. This is Australia. So most regions of the world, coastal regions, are at risk of impact of climate change and sea level rise. I show you information from Africa because it's peculiar. Even from the morning discussion, the energy perspective, we saw the statistics from Africa in terms of energy was very low. In the same sense, we have a huge capacity in Africa that most cities are recorded as the fastest growing, at a faster growing rate, and that's by 2050. It will be, that is recorded. And this growth is in terms of population, of course, infrastructure, and migration, social settings, and even policy intervention. So more attention is going there because it's the opportunities for growth that side. In that same sense of growth opportunities, which means that we have the opportunity to create new things, to do new things for the changes that we want, because the opportunities are available. And the cities in Africa being the fastest growing areas, which also give us the opportunity to economically make the impact that we want. So from the report, we're going to have vulnerable cities that are at threat with coastal erosion, urban heat. Most cities in Europe, in this year especially, we heard of the heat waves that affected a lot of cities, and migration is going to affect most urban areas. Water resources is going to be impacted greatly. And I said earlier on that most cities in Africa have limited adaptive capacity to withstand the impact of climate change or extreme weather event. So it is important to build resilient city. And building resilient city is encompassing. It's all involving, include the earlier discussion on energy, including building the cities to be able to withstand the impact of climate. This is just a picture to show you at the moment as we speak the impact of coastal erosion and coastal flooding in Ghana. So these are cities, or this is a picture from a city in Ghana I took just in the course of the week. These are coastal areas in Volta region of Ghana. It's all over in the news. The whole settlement, various cities along the coast in Volta region, taken completely by the sea in that sense. And it's not in a small areas, very huge distance from the sea, or you can see the houses beyond all these areas are taken over by the sea. So 3.3 to 3.6 billion people live in hotspot areas around the world, and these are all vulnerable people in the society. And definitely we have to do something. The essence of COP, the essence of our research is to impact society. So I will soon be ending, but then, these are still the implications of climate change on cities. So this risk will expose and amplify the already existing stresses in our societies and cities. Poverty will even be more, and especially Africa, where urbanization rate is high. We have huge migration from the rural areas into urban areas and putting stresses on infrastructure in the urban areas already. And so climate change is a multiplier of poverty and making the poor even poorer. To create resilient city or to build resilient city, we need to put, as I said, all-encompassing structures that will make the cities be able to respond appropriately, to rebound, recover quickly after impact of climate change. So, resilience, we talk about the economy, how the city is growing. As I mentioned earlier on, urbanization comes with economy, the society, the economic value, the household income, and all of that type of employment that are available. Then governance, the policies that are implemented that's protecting the citizen, protecting the environment, or helping the public sector respond appropriately to the issues of the city or areas. Then, of course, the environment, how we are building our adaptive structures. So all of these four components must come together to feed into the resilience of a city when we are building it. I'll move a bit forward. So we are guided by mitigation and adaptation. The same discussion we are having, although we're trying to build a resilient city, which means that we're putting up adaptation structures that will help cities recover quickly from the impact of climate change. But we're doing this with mitigation also in mind. And whilst we're trying to adapt, we should also be thinking mitigation and acting mitigation as we do. So the two must go hand in hand. Now, just to mention to you on the IPCC's special report on climate change impact on cities, this is a new call, and we just called for nominations between October and November. Currently, we have started the selection process. We have received 1,250 nominations already. And this time around, a critical thing we have decided to do is to include practitioners in the cities. So people who are working in the local government, assembly level, community level, we need to define the topics together. It shouldn't be scientists only preparing what we think is prudent, but sit in the same room on the same round table with them. Implementers of these policies or this report together to define the topic. So scoping will be in March 2024. We are still thinking through the venue or which country is hosting the scoping. So this is the few highlights that I thought I should share with you before the panel will start the discussion. But again, on cities, all of us have a contribution to make. So if you're already not nominated because it's closed, you can still be nominated to come in as a lead author, as a reviewer, as any level at all to contribute towards. Your papers must also be available for us to cite or to review as part of the report that we will write for the city's special report and any other report in the 7th assessment cycle. So that's it. Thank you. And on that note, I think I'll go ahead to invite. Thank you. Okay, you want to come in? Sure. So I will invite my panelists, Hassan and here. Please come over and you introduce yourself as you sit and yes.
Thank you very much. Thank you for the presentation. Let me check if this one goes. Yeah. Okay. Thanks. My name is Hassan. I'm very excited, but also very daunted. Excited because as a student of science or aerodynamics, which I did my undergrad, and I did a PhD in fluids of turbulence. I'm excited to be reconnected back to my roots, because that's where I started. So I'm very excited about that. That brings me back to my roots. I wanted to become a scientist in my life, but have diverged and become a management consultant. So that's why I'm excited. But on the other hand, I'm actually quite daunted, because I look around and see, oh my goodness, professors, statisticians, research, amazing group of intellectual figures in front of me, and here I am trying to say something about my point of view, so I'm actually daunted about it. So, bit of introduction. I am a management consultant. I am a strategy consultant with Ernst & Young. We have a strategy arm called Parthenon, and that's where I work. I've been a consultant for more than 25 years, back in Australia, Southeast Asia, and here for different companies. And for the last decade and more, I have been working entirely in the energy value chain. So energy, oil and gas, chemicals, downstream and everything, utilities to some extent, and hard-to-abate industries. I'm an engineer. I love that space. So that's where I've been working. So what I wanted to talk about today is really the energy transition. I'll share some slides which is really around transition, how it's happening, some cost downs, some projections, and these are known. The point is not to introduce another point of view. The point is for me to use that as a backdrop and generate some discussions from the topic at hand, which is really from the societies and cities and our lives perspective. What does it really mean? So when you look at my slides, don't kind of look me down like, why is this 14%? I thought it's 18%. I think that's not the issue. So to start with, as we kind of look at the energy sector, what is really happening and shaping the world that we live in today? And there are 5 kind of key thematics that we are kind of living, and it shouldn't be any surprise. Right on the left-hand side, geopolitics. It is becoming a day-to-day situation of geopolitics that's kind of changing the landscape from supply-demand dynamics, pricing, there's disruption in the landscape. Because of climate action, sustainability, topic of climate has now become a boardroom CXO ministerial level agenda, which was not the case even 5, 6, 7 years ago. It was there, but not at this level of importance. So that's become very important. I think we started to talk about people's attitude. I think that attitude is also changing. There were times where we thought, are people really interested in this topic? Are they taking it seriously? Are they going to pay? Ultimately, me as a consumer, I might pay for my pocket. Every day I'm making a vote. When I'm using my dollar to buy a good or service, I'm actually making a vote in terms of what I'm doing. So I think there's a bit of changing happening in that direction. For me, what's interesting is to observe the convergence that's happening from a traditional definition of industries. We're used to saying, here's an oil and gas industry. We're used to saying, here's the electricity supply industry. We're used to saying, here's the automotive industry. Actually, if you look at it, it's all collided. EV, if you look at EV is a phenomenon that brings together electricity industry, that brings oil and gas industry, that brings automotive industry all together. So no longer the traditional boundaries of industries are very clean. I think they're all colliding with each other. Finally, technology. I think we've heard a lot of things around technology, not only from a core clean technology, different technology perspective, but also from a lot of digital technology perspective, which are part and parcel of making it happen. So I think we live in this kind of world whereby the transition is kind of moving ahead. And what does it mean for us? Some of the stuff that I've written here is that there is no single transition. Depending where you are, which part of the world, which part of the industry you are, is very different. Speed will vary, and that is have an implication for where we live. Industry and consumers, I think we'll lead the change. Molecules will become greener, and it has a long way to go. So I just want to stop there for a moment. I think these are not new stuff that I'm saying. I think if I pick up the last one, the transition has a long way to go. 2030, 2050, 2070. In fact, this is the reason why it is important to think about is it is no longer an energy transition. It is actually a whole of society transition that we're talking about. Because sometimes you say, okay, energy needs to clean itself. Yes, but we all have to come together along the journey. For example, look at this room. Every bit of thing has to change. Everything has to go circular. I mean, your point about not linear but circular. So I think that's why this transition has a long way to go, purely from making it happen. Forget about Forget about the policy, forget about technology, forget about willingness to invest in political will. I think we're talking about a massive, complex system globally to move. That's why it's going to take a long way to go, and that's why, from cities and lives perspective, this is going to be very messy as we go forward. The other one I'll pick up is, okay, I'll come back to this later on, because I work in the oil and gas industry quite a bit, and not that because I work in this industry, I'm a very objective, because my training is in science, I take a very objective look. So I'm going to talk about what does it mean in that regard. Again, a projection from our knowledge team that we have internally in terms of where is this heading. And again, if you speak to different organizations, all have their own projections, right? So I'm not saying one projection is right or wrong. I think that the argument here is the direction is correct, totally correct. For example, we can say that the oil and gas share is going to decline now. Is it going to be 20%, 30%? Anyone's guess. There are some modeling that's been done, some assumptions that's being done based on that. You can decide that. Clearly, electrification is going to go up. Is driven by solar and wind, and we forget hydro most of the time. Thank you for reminding us. Now, my point is, this whole oil and gas is here to stay. No doubt about that. But then there is this whole noise goes on one side saying, kill oil and gas. Okay, I am happy to hear that if you killed oil and gas today. Well, first of all, the oil and gas has survived because we have consumed oil and gas. So don't come and blame oil and gas industry because they are the producer of it. We are the consumer of it. So kill oil and gas means that kill me as well. That's number one. The second thing is, if you want to kill oil and gas altogether, it's not possible to replace the energy network system that's currently existing in the world in its way, in terms of infrastructures, pipelines, storage tanks, and whatever that we need overnight over the next 10, 20 years to take out every bit of thing and bring in electrification. And even if you brought electrification, it's not going to solve the world's problem. So oil and gas is here to stay. Now, I want to look around this room. I want to sit on this chair. Wow, look at this bottle. This is plastics. Where is plastics coming from? Oil and gas. You look around everywhere. Building paint. Okay, this is a paint, right? Yep, this is paint. Paint is actually polymer resins. Whether acrylic paints or a water-based paint, it is polymer resin. Where is polymer coming from? It is coming from oil and gas. You're sitting on a chair. It is coming. So we don't realize how pervasive oil and gas has been in our life. Because if you say take out oil and gas, yes, you can, but you cannot take out overnight. It's going to take decades to get there. So my personal view of looking at everything is that it's here to stay. The key name of the game is to make it much more cleaner, much more sustainable, so that all the modes of energy come to and survive together. And that is an implication for us as how we live our life. So then, as we look in transition, some of this stuff are not known. So what does it mean in terms of change that is happening? As I said, molecular energy, oil and gas is nothing but molecules. They will be here for a foreseeable future, we like it or not. Renewables is becoming mainstream. Now, the implication of that is we will start to see a lot of energy storage application. You highlighted hydrogen as an application on the far right-hand side, but also we have other kind of battery applications. So we will see in our lifetime different kind of storage application, different kind of systems coming in, which will be part of a life in our house, in our work, in our kind of society everywhere. So that's the kind of implication of it. Almost everything is electrified, very true, but we can't electrify cement plants. We can't electrify steel plants. We can't electrify petrochemical plants that are producing major building blocks of the society. So what do? They will have to be taken care of. This is happening already. Energy is localized. I think a lot of people have got distributed energy. If you look at this country, a lot of distributed energy, rooftop and solar. In Australia, where Abu and I are from, we saw a wave of distributed solar on the rooftop. I think this is very true. If not us, our kids are going to lead the way, for sure. I mean, those of us who have got kids in school, they are much more advanced, much more pro kind of climate-friendly, environmental-friendly. So they're going to lead the way. Grids, is a major roadblock at the moment. Yes, we can plug in X amount of production capacity generation capacity, but the grids that transport this electricity from one to another cannot deal with that. So the moment you bring 30% of mix of renewables in the grids, it starts to fail. The 40% maximum. But then now if you go 100%, the grids cannot do it. So I think there are some problems that we see. And ultimately, it's all about the integration of the old and the new. So I think this is the implication, but it also means how we live in our day-to-day life, how we go to work, how we do things will change. I think I'll skip this. This is about renewables becoming a dominant. It's fine. So we've seen these curves. One of the good things about this whole revolution that we're seeing in terms of transition is that ultimately is an economic. The moment the economics are good, it will switch over. It doesn't matter how fancy the technology is. The moment it is in par with economics, it will switch over. As simple as that. So we've seen solar, onshore, offshore coming down, and probably will come down. We also know that is now going upwards a bit because of also supply chain issue, cost inflation issues. So I think that's an issue. Now, if you look at hydrogen in a similar way, that I think you are an expert in hydrogen, costs are very high. The issue at the moment is we're not able to scale up. Because if you don't scale up manufacturing with high volume, we're not going to see the learning curves coming down. So I think, yes, we have seen this. There's an expectation of costs coming down, but I think we are still not there yet. And to make the point even more, if we live in certain parts of the world, we'll see different kind of transition happening. So for example, what is this chart telling us? These small bubbles are telling me in US, currently I have got a lot of gas, but I think it's going to get much smaller. Same thing. I think good thing is that I think as a trend, except for China, coal is going to getting reduced. I think that's, you mentioned, right? That's fine. Whereas nuclear, still not there. I think, you'd love to see a bit more nuclear, I would imagine, right? Wind definitely growing, solar definitely. So if you are living in Europe, the way the energy that's going to come to you versus if you are living in other parts of the world is going to be very different. Very different. So what does it mean for us when I'm sitting here as a consumer? I will have choices. I will have choice in front of me, hopefully down the track, whereby the energy retailers will be able to provide me, okay, Hassan, you want to buy energy from me? I can give you a green energy coming from wind, or I can give you energy coming from hydrogen, and this is going to be the differentiated tariff. So that's what's going to make a difference in terms of our life, because the whole energy system is changing. But I think that's when people say it is very different from a different geographic perspective, this is probably what's driving it. Again, we are growing, population is growing, the demand for electricity will continue to grow. So when we looked at where it's coming from, majority of it's coming from the industrialization of our world, not from other spaces. So what does it mean? It means that yes, industry will consume more electricity, and hopefully if it's much more green, that's better. But I think, for example, in this region, if you think, those of you who have been living in this region, and Abu, you've been here and others are here, we have been seeing massive deployment of capex to diversify the economy, to make it much more technologically advanced, much more industrialization. So that will require energy. It's probably part of it. I'm saying not all of it. What does it do? It forces us to think about how to make those industries far more greener than their predecessor industries. I think there's a duty of care here. The other one is it's also creating jobs. As industries are being created in this country, there's a huge push here in UAE, in Saudi, in all the other GCC countries of industrialization. There are ministries for that at the moment. So it creates more jobs. So from a society's perspective, yes, this push is actually creating more jobs, more economic activity as well. My favorite topic of oil and gas. So what is it trying to show to you, sir? Okay, typically, an oil and gas company, as example, right, has a mixture of oil and gas and really slightly bit of some sort of renewable bio, right? But if you move forward, a typical oil and gas company going forward will be not an oil and gas company anymore. And this is happening in this part of the world. Or those of you who are here in UAE, you see ADNOC. Those of you know of Aramco, and I do work with both of them. They are massively trying to do something fundamentally different. They've set up the new energies businesses, which are going and investing in hydrogen, CCUS, renewables via Masdar over here. So, and synthetic fuels. So when you say kill the oil and gas company, you're talking about killing all these other sectors as well. So my myth-busting request is that please don't kill oil and gas company. They are here to also help for the future, because as they go along, yes, their returns will be reduced, but they will have this kind of portfolio going forward. They are working on SAF. A lot of oil and gas companies are partnership in SAF. Yes, we can't produce electric planes, but hopefully we can produce more sustainable fuels. So my point is, as this industry is moving, they're also transforming themselves, and they're also part of the solution from what I can see. Not because I'm a consulting to this industry or chemical industries or cement industries, purely because I see this is where they're going, and they're also part of the solution. So one of the myth-busting that I wanted to help encourage us to consider is that whenever we hear oil and gas is the problem, actually they're also part of the solution. Finally, some charts about the consumer trends. So you can see from left to right over the 2025 in the future, and this is based on some statistical data and interviews that's been done globally, the perception, there's going to be huge uptake of EV, and that's very clear. I think this trend is secular and people know about it. But also in terms of other forms of heat pump adoption, is going to, particularly I think Europe is going to take a lead, followed by other countries. So consumers are starting to take a lead in this one, in terms of adopting newer technologies. Governments are making incentives for that. So this will continue. So I think ultimately a lot of things will boil down to who we are and how do you make the vote with our dollar from the pocket and make this change enabled. So I wanted to use these as a backdrop, not so much to re-educate ourselves, because I think all of you yourselves are educated about this whole transition, the mix of it, what's really happening. But I just want to bring a different flavor from the same view, but more so from what does it mean for me, what does it mean for the society going forward. Final comment on this one, and maybe we can discuss a bit more. As the whole energy system is transitioning, I think it's gonna get bifurcated by some structural differences. Why do I say that? If the clean energy system is founded on having access to clean solar and wind and water, so regions where we have this plenty, regions where we have an ability to store carbon will be far advantaged than regions which don't have it. So then we're going to create an energy system which is then structurally going to be very different from what we see today. So, okay, fine, but it will potentially create energy poverty depending on where you are. So I think that's a huge issue in terms of society at large today, because let's say I'm going to use the example of Africa, right? Let's say there's a developer that goes to Africa, fantastic, low cost, low environmental restrictions, boom, I go and produce my hydrogen, I ship it to Europe. What have we done? We have created energy poverty even more, because now the energy that was supposed to be provided for trilemma solution for that country is even left behind, because at the expense of that country, we are making energy trilemma met for other parts of the society. So I think there are some severe consequences in terms of this whole transition that we're going through from a society and from cities and livelihood perspective, which I don't think people are talking as much yet, because people are very busy trying to find the technical, political, policy solutions without worrying about the unintended consequences that's going to come. And then you're going to be saying 20 down track, oh my God, we're trying to solve for carbon and the world, look what have we done to the society. And that's exactly what has happened in the last industrial revolution. We have solved for productivity, technology, 30, 50 years down the track, we say, oh, we have made a big mistake because we haven't thought about the impact for the environment. So I worry because when we're now solving for environment, 50 years down the track, I'm going to say, oh my God, what have we done for the humanity? So I hope we don't do that. And with that, I'm just going to stop, and hopefully we'll get into much more interesting conversation. Thank you.
Okay, so I think, Abel, you can go ahead with your talk. You first introduce yourself, and then you talk briefly before we go on the panel, please.
Thank you, Professor Nata. Assalamu alaikum, peace be with you. My name is Abu Bakr Chaudhry. I represent a funds management company. This fund management company is set up by Public Investment Fund of Saudi Arabia and Islamic Development Bank, with joint collaboration with the other sovereign funds in the region. Primary goal of my company or my fund is to invest in Islamic economies for their infrastructure development. And it has two metrics. One is it should be commercially viable, and it should help the Islamic countries' growth of GDP. Just a little bit of a historical background. If you look at any day, the share of sovereign wealth accumulated in the world, 60 to 70% of the sovereign wealth resides in Islamic countries. And if you look at the capital needs or capital-hungry economies in the world, it will be predominantly Islamic countries as well. So it's a topic that Hassan touched on, saying that when we are transitioning into a cleaner economy, are we creating poverty, the energy poverty? Similarly, there is a disparity within the Islamic economies, the share of wealth and the capital deprivation. So Islamic Development Bank trying to build a bridge, and we are a very tiny initiative of that, headed by the Crown Prince of Bahrain. That's why our head office is in Bahrain. With that, and I want to take a couple of points that Professor Nana and Dr. Hassan shared. I'm neither a physicist nor a scientist. I'm basically a financier. So my experience is more on the road and the practical world. So I'll share a couple of initiatives that our fund has directly been involved in terms of energy transition. And particularly with Professor Nana's point that urbanization and how the cities are coping with this issue that we are globally facing. Urbanization is an interesting part because people started thinking about that industrialization is moving people from the agrarian society to urban society, and China is a great example of that. But added to that is the climate situation that it's creating in the coastal areas. I spent my adult life in Australia, but I was born in Bangladesh, and you could see on the map that Professor Nana has, it's a very dark color and a very dire situation there going forward. So that in that urban environment, how people are naturally coping with and how government has woken up. One of the examples of that is what I'm going to talk about. And so it's a specific example just to illustrate that people are moving naturally towards a cleaner environment or transition of efficiency. And the other example that we are involved in. I'm not going to show you the detail of it. It's so ominous around us. Is that the solar and wind energy? At the start of probably 10, 15 years ago, the components were very expensive, and everybody is saying there's not enough land, not enough solar power, not enough wind. Is this going to happen? But as we all know now, the component prices of both solar and wind has come down sharply. In some cases, it's even cheaper than coal. We are all surprised to that. And it's not only the government that now buying funding these initiatives, even the large corporations like, for example, Amazon and Apple, they're directly buying from the generation providers like our fund, buying from solar and wind generation companies directly, not even the government. So it has moved down from G to G to B to B, and it's going further down, as Hassan mentioned. So coming back to the topic that I'm going to discuss with you today, is that this is an example of how Saudi Arabia actually, in multiple fronts, active, and UAE as well, and all the GCC countries, even though they are predominantly oil and gas resource rich, but they have woken up massively, and they've taken it really seriously, that how not only that they will transform the society ground up, literally. They're building, you heard NEOM, and now you see in UAE many cities and Knowledge City here. And the government has come up with a directive about 10 years ago, and now in 5 years they're implementing it, is that if you look at UAE or any other countries in the world, the actual usage of electricity that Hassan talked about, 60 or 70% is actually in these countries, in the GCC, is actually cooling, utilized for cooling. So that's a massive component of the electricity generation that goes into these countries for cooling purposes. So Saudi has made a conscious decision for their government facilities, military and industrial facility. And in previously or traditionally, each building would have, I'm sure, this building also has a chiller on top. And so what the system that we have invested in, and it's one of the largest district cooling company in the world. And so the practical experience is that if we adopt the district cooling, means this entire area in Knowledge City could be cooled through this technology, as opposed to each building of this Knowledge City would be cooled by individual plants. And that cuts down the electricity consumption quite a bit, and also the cost-wise, it is 50% reduced. So the Saudi government and UAE and Oman and other GCC nations are really pushing this kind of technology. Not only that they wanted to transition into an energy efficiency, but it's a practical way of utilizing their hydrocarbon resources, burning rate. So that's something that I just wanted to, if we could go the next slide. Oh, it's there. Sorry for that. So as I was explaining, that as opposed to a single chiller of these buildings, if you could centralize the cooling system, and that could cut down the efficiency, increase the efficiency quite a lot. I'm not sure how the, yeah. It's just illustration only. It's not. So I'm just trying to explain how this cooling system works. In a normal cooling system, you would take the air and cool it down, and the coolers have to be cooled down in a normal, through conventional technology. But in this technology, they use cool water, and these plants are centrally located. So if this building, for example, at any given day is not totally filled with its inhabitants, then the plant could then detect intelligently and say, we wouldn't cool certain section of this building, as opposed to a chiller on top. Whether there is a single human being in the building or not, they would cool in the same degree if you run the plant. So that way it creates efficiency, flexibility, and it's just how this system works. Next. And there's some statistics about how this conventional, as opposed to conventional cooling, this is system, how it is factors of recursion, and then how this, I don't want to go into the technical aspects of it. It's just a much more efficient way of doing it. Next. And the concept is why, as you could see, that it is a water-based recycling technology, and it's environmental friendly. It's energy savings, as I mentioned. It creates more efficiency. 50% less than consumption in a normal conventional cooling. It has better density and user comfort, and so on and so forth. Next one. So there are other system advantages. If cities and bigger areas like specialized zones like this adopts this technology, then it can be powered by renewable energy, peak load, and it is greener, considered as a greener buildings, and the heat is not wasted. But in a normal cooling system, you take the component of air, cool it down by way of taking out the heat in this, and then release the heat in the environment. But here in this system, because it's cooled water, there's no heat extraction, so that saves the CO2 emission. Next. Yeah. So, is it power efficient cooling system? I think that there's enough scientists in the room. You would be able to work out it better than I could. Some of the statistics. Next. Yeah. So that's the fund that I represent. So what I was trying to demonstrate that what Hassan said and Dr. Nana mentioned, it is no longer a global phenomena that we listen on radio or watch on TV or come to this Stockfest. This is a practical problem, and I think every part of the society is trying to do their bit. But whether we are going to get there below 2 degrees, this decade, it's beyond my kind of level of understanding. But I think that we are running. Everybody is aware, and it's good that even a remotely scientific venture like ours are also invited into recognized by the Institute of Physics. So I'm really honored to be able to share our practical experience with you all. Thank you.
Yeah, please don't go. Take your seat. Hans, please come. Is it Hassan? Hassan or Hans? Okay. So thanks very much for your overviews. Just one question you share your perspective on, and then we take questions from the room as well. On the trilemma, energy poverty, energy demand, zero, net zero, emissions. So I need you to share your perspective based on geopolitics, your specific expertise, and looking at opportunities in the cities. So you can pick it from economic point of view as well, but also from your various expertise. Then I will open it up for the room. I have so many questions, but I don't think time will allow us. But for this, I need you to share your perspective first. Thank you.
Okay, thank you. I think it's a very important and a very complex question because we talked about the trilemma. We talked about the trilemma and then energy, poverty, and the net zero stuff. The way I kind of look at it is that absolutely we work in a geopolitical environment that's very uncertain and it's almost like it's very difficult to predict what's going to happen, but what is for sure is that this is going to remain. And we'll continue to see polarization as a result of that, of economies. We'll continue to see polarization or dislocation of supply chains and stuff like that, because a lot of people will insure the supply chain because they want to protect the disruption coming in from that perspective. So that's kind of the landscape. Now, if I am sitting from a trilemma question perspective, I think it's very country or region specific, and at what level of maturity the country is. If I take example of any Southeast Asian or any Asian countries, I think for them energy security is more important. Energy delivered at an economic affordability is more important than sustainability, because they have to continue the economic journey. Whereas if I look at Europe, it used to be energy security, sustainability, but I think now it's flipped. I think energy security has become so important because of the geopolitics. If you look at Africa, I think energy affordability and security is by far because there's still a lot of areas of Africa that needs to be electrified and getting. So I think to your question about this trilemma, I think it's very dependent on which country it is or which region it is and what level of maturity. It's like Australia, where both of us call it home. I think it is about sustainability at the moment because we have energy security, we have a certain level of energy prices. Now it's all about how can we really make it much more sustainable. So that's kind of my reflection on. It's very geographically dispersed. Now, how to solve this issue of energy poverty? I think this is where institutions or programs like COP and other multinational institutions come together and trying to create a balance in the world, because otherwise I do not want to be growing at someone else's expense. I think that's why there's an overlay of institutions that come together and trying to bring some common understanding. That's my personal way of looking at it. Yeah. Hopefully that gives a bit of insight. Thank you. It's a very tough one. I don't think if anyone has solved the question, I'm sure.
It's actually a tough question, and I think whatever it is, we have to be talking about it until we find the solutions, whichever way possible. I am just thinking about time now, but you can share your perspective also on it.
So I think one of our earlier panelists made a very insightful comment, is that no power is more expensive than any power. And I think you mentioned that. So on that question, I think I wanted to make the comment on more specific on the energy poverty situation. I think there's a debate rating those who can, developing nations who can run towards energy transition. Then what happens to countries like South Africa? 70% of their electricity is generated through coal. And why is it? So is Germany, but used to be. But why is it now? Because that's the resources they have. So for their economic development, the globe has to, or this global forum has to understand that this transition, meaning them running their energy, ensuring their energy supply, and gradually how they can do it. So that may take longer than somebody like Japan or even Saudi Arabia, who has all the money under the sun to run faster. So that those debates, hope that doesn't become a situation whereby a division between global north and global south and all of this politics. So that's something that people should, the global leaders, as not addressing yet. And the other question that actually Hassan mentioned is very interesting, is that I take a leaf from Elon Musk and his consciousness about AI security and what it does to the AI development. And I think this question about energy poverty and what happens in the transitions, nobody is talking about it right now. I think there should be come out more now than 50 years later, as I mentioned.
Okay. Yeah, thank you very much. As we speak, many scientists around the world are signing a position paper on the phase out of the fossil fuel. So I know there's, so at the moment, energy is security in some regions, it's luxury in other regions. So it's a question of distribution or balance of energy in this sense. So now I'm thinking, trying to, if we are more prudent on the phasing out of fossil fuel, which you don't completely agree, I understand, will you recommend a radical effort into CDR in this sense, carbon dioxide removal? Because I completely agree with your perspective that we can take out fossil fuel completely, then nothing works again, because it has infused into our economic system so perfectly, and taking it out to be a complete disaster. So now, what is the way out? We still need net zero. Sure. From the IPCC special report on 1.5, if we don't phase out fossil fuel by 2050, we're going to have more devastating impact than what we are even having now. So then we need to do something. Sure. We need to act. How do we go about this situation? But I'll still open it up to the room for questions or contributions.
It's a very complex question.
I need to be
I think you're asking another tough question, and we're not able to answer fully. My personal perspective would be that if we want to phase out fossil fuel, not fully, but as much as possible, then few things need to happen. To Professor's point, I think we have to rely on technologies that allows us to take carbon out from the system. In fact, if you look at any country or I do a lot of consulting with companies about net zero strategies. So you can do energy efficiency, portfolio optimization, you can do electrification, but there's still an amount of carbon that you can do nothing about.
Yeah.
So you have to bring in technologies like carbon capture or direct carbon capture to kind of take care of it, and you have to bring in carbon pricing ultimately to incentivize non-new technology. I think these two things need to come in hand for us to have a chance of accelerating the curve that we're going to. And at the same time, all the oil and gas companies who are producing oil, which will they do, will have to continue to accelerate their decarbonization so that any bit of oil that's coming in are much more sustainable. In fact, my personal view is that the quicker some companies are producing much cleaner hydrocarbon, they will be able to charge a premium, because the world, you'll see a bifurcation. It's almost like a higher grade commodity versus a lower grade commodity. So I think the market itself will bifurcate, and it will drive towards that as well. So I think there's no one answer. It is a combination of some of these levers coming together and push us much more quicker to that journey, and hoping that we still exist, our children and the grandchildren still exist, can live in a habitable land in the next 30, 40, 50 years.
Yeah, thank you. But then, yes, Prof.
Question to all three. I mean, just gone green. Question to all three of you. Well, three questions to each of you. One each to three of you, if I may. Let me just pick up on the fossil fuels problem question that we all face. Last week, the United Nations Environment Programme released a report which looked at the plans for all governments and showed that by 2030 there will be 110% more fossil fuels in production, in use, than is consistent with 1.5 degree. Right? That's what are we now, 23? That's 7 years' time. There's 110% more than is going to be consistent with 1.5. And we all know the irreversible tipping points that are looming, and we'll hear more of those from Professor Miles Allen later this afternoon, I'm sure. And so while, Hassan, you articulated and laid out scenarios and pathways which are plausible and consistent in terms of the energy mix by 2050, already we see that the plans are inconsistent with that. And here's the other thing, 151 countries signed up to net zero targets. The same countries who are signed up to net zero targets are now saying, or putting in plans that are going to increase fossil fuels by 110%, are way above. And by the way, that also leads to a 69% or approximately 60% chance of not hitting 2 degrees either. Okay, so it's not just 1.5, it's the overshoot. Now, on the other hand, yes, absolutely CCS, carbon capture, utilization, storage and reuse and all of those things. But again, the various scenarios that I've seen, and please anybody else correct me if I'm wrong, but are that even in the most optimistic scenarios, you're never going to have deployment of CCS faster than the increase in the fossil fuel use. So you're still going to be overshooting. Exactly. So what the heck do we do? Carbon pricing is one mechanism, but the world can't agree on it. Exactly. And it goes back to the panel that we had at the beginning where Charlie talked about the lack of political leadership in some sense, because that's what it's going to take to address some of these problems. So I'd be interested in your thoughts on that. So two other questions, if I may, very quickly while I've got the microphone. One, I'm interested, Abu, as you're a financier, and you come here talking about the deployment of capital into obviously really cool technologies, good technologies and good district cooling, which makes sense at the city scale and at the district scale. But I'm interested in the flow of capital more broadly as you see it. Enormous amounts of capital and private capital are going to be required to make these system changes that we see, that we know are needed. In your experience as you go around the world as a financier, as an investor, and you talk to governments and sovereign wealth funds and investment agencies, do you see an appetite and a driver above and beyond just pure commercial returns? Right, so that's a question. And then, Professor Nana, I'm intrigued by, you're an atmospheric scientist. You were co-chair of the working group 1. You're going to be involved again in coming through. What role is there in Ghana for physicists in adaptation? How is your voice heard, and what role do you play in putting strategies, plans together as a physicist who works on the mitigation side, but actually needs to cross over into adaptation as well? Thank you.
Yeah, so if you want me to go. No, thank you. It's an interesting question. Our life has become a bit harder because now not only that we have to be commercially savvy, we also have to bear in mind that it is quite a bit the metrics that I get paid is sustainability as well. So there's another metrics added to my performance is it has to be adding a GDP growth to the country, it has to run commercially, and it has to be sustainable. Now, I wanted to refer to, again, the earlier Leonard Tanner mentioned about nuclear, for example. We do see a lot of smaller and modular reactor that's been talked about. So that's where we're looking at. But it's not I think it's not so much of security of nuclear plant, it's most of spent fuel what we do with it and where do we store in it, not dump in some horn of Africa. And so that's where the hesitancy between, and where I adopted home in Australia, I shut down nuclear operation, and I don't think the people are willing to go back. That's again a political question as well, that even the government wants to put up a nuclear plant, people are in arms. They don't want that. But I think that's changing with nuclear fusion. I think the UK is putting up a lot of money, and we are looking at it. But it's just not there yet in commercially. So I think that to answer your question, 10 years ago, there wasn't a political will for sovereign wealth funds and government to allocate capital towards energy transition. Today, the issue is quite the opposite. We have political will for sure. We also have trillions of dollars ready. We don't have enough commercially viable opportunities to put money in. So this is another new conundrum for financiers. Where do we put money in? That's very hard for us to do that.
Good to have a friend who's a financier, because when I go and talk to developers and governments saying the financiers are not coming to the party because they're looking for returns, right? So it does become a chicken and egg situation as to how do you solve this problem. So the breakthrough is then someone like government or someone else to come in with some patient capital and say, look, I'm going to plug in the patient capital because I believe that it's needed for the society, and probably government and other agencies can do that because they're not looking for an economic return immediately. It's like building out the infrastructure.
So on that,
then hopefully then you guys will come and invest.
I make a point on that. I think although we hear a lot of dance around in the UK politics, but Rishi Sunak actually has done that. He has put in $1.5 billion and appointed the vice chair of Oxford University to do a commercially viable nuclear fusion initiative. And then when he called us, I got a call like any other. We were all ready for the check in hand, but it's just not there. So there is no shortage of
Other example is, I think everyone talks about USA at the moment. IRA is a big lever that has come on board, and previously projects that were not economic has become enormously economic. So you can see how capital is now flowing into USA from other parts of the world. So that's an example of how, despite all of these kind of constraints and barriers, there are tools and mechanisms to move this a bit forward. Keeping in mind that governments will always take care of its citizen, like, in UK where you are from, households are being impacted by multiple of energy bills, right? Yeah. Because of
but also, as you correctly said, it all boils down to be honest, I am far behind as a financier or a scientist or forefront, but the key actually, the consumer holds the key, the next generation. If you vote, as the Economist said, Paul Samuelson said, vote with your dollar, right? If they start asking for it, government will come. But whether that satisfies the scientist's perspective of the 1.5 degree, that's a big question.
Yeah, but Hans had said that because we have demand for fossil fuel products, that's why the companies are also producing. So maybe when we stop demanding, we will then collapse the companies automatically without even discussing it at all. But just to, come on the issue of the CDR before I answer the physics question in Ghana, I feel that at the moment, there is the potential in the, should I call it geoengineering and carbon dioxide removal, decarbonization, all the technologies to help with the removal of carbon dioxide in the atmosphere. But what we are facing now is the ethical challenges that we have in practicalizing some of these technologies. So at the moment, we have seen in the models that it's possible to do cooling through these technologies and also remove carbon dioxide and all of that. But more of the discussion is about the ethical issues around it. And scientifically, we also completely understand. We can have the immediate effects of cooling. For example, solar radiation management. We have a natural system in West Africa, Harmattan season, where there's natural harmattan in the atmosphere and it brings cooling. So from the modeling part and science part, we are looking at how can we implicate this process all year round or even across other regions. So putting aerosols in the atmosphere and bringing cooling. So our headache is the global warming. If we can cool the globe, and so then other technologies of decarbonization and all of that can also come in. But we don't know the long-term effects these can have on the climate system. So we are a little bit not so sure of how to go about this whole thing. But if we are sure today and then we start the process, I'm sure we will not get to 2050 to be able to get to net zero maybe or cool the globe. So we are still in that dilemma as even scientists as to how to go about this whole process. Now coming to what we do as physicists in Ghana, we provide the scenarios, the projections for the various sectors. So impact assessment, we do vulnerability assessment, exposure for the various sectors for planning. That is from our side. We have research into materials that resilient to environmental hardship or hazards, excessive heat or flooding, so let's say building materials, for example. We have also supported coastal erosion solutions. So government is building sea defense and the materials that they're using, we're looking at the sustainability of these materials as well. So what they're using at the moment are big rocks, and then we see that they are not sustainable because the ocean itself is taking the rocks away or they're eroding the rocks themselves. So we're looking at other ways of more sustainable solutions to these ones. But our core activities or influence on the discussions on climate is more of the modeling, providing the long-term solutions or long-term predictions for planning for government. So we contribute also on the national circumstances to the UNFCCC and looking at the impact of climate. So one research is also on the Harmattan, the solar radiation management, but in modeling sense, it's completely fine, it works okay, the cooling and looking at the influence of the aerosols on other climate variables, humidity, wind, looking at rainfall as well. Temperature is so clear. We have a paper coming out very soon on that as well. So we're trying all these various ways in our contributions from the physicist point of view, but there are also the impact group as well who are doing the more detailed assessment in the communities level. Yeah. So thank you. We have our time is up for lunch. Huh? Okay. So thank you all, and then thank you for your attention as well, and thanks for your question. Thank you.
Thank you very much to the Institute of Physics for the invitation. And also, I should say that I apologise that I'm having to represent Tim Palmer here, but I will be. He's given me some material that you'll see. I'll highlight the material that Tim Palmer has given me to talk about in the course of this talk. Although I couldn't resist putting in some other work of my own because people like to talk about their own stuff. And although it's work I'm doing with Tim as well. So, I mean, you've heard enough already this morning. This was my context slide, thinking I was the first talk of the day, but, you know, our world is changing, we know this, and it's all warming up. Important context, of course, is the regional variations in how the world's warming. Again, this is just observations, trends up to 1980, and the rate at which the trend has accelerated since 1980. So this is warming rate in degrees per decade since 1981. And you can see that, you know, we've got some parts of the world, particularly this one actually, the Middle East, North Africa region, which is warming at a fair clip, 0.4 to 0.6 degrees per decade. That's twice the global average rate. For reasons I think it's fair to say we're not entirely clear about, and I gave myself the title of the next challenge for climate physics here. And I think understanding these sort of regional subtleties in what's happening to our weather is actually the big one of the big challenges we have. There's another big challenge, of course, for everybody else down at COP to try and do something about it, and I'll talk a little bit about that at the end. But the focus of this talk mostly is on understanding what's actually happening to our weather. It's, of course, not just the overall trend, but what happens in individual years. And we've just gone through the hottest year on record, and we had the hottest day on record in the middle of this year. That's annual daily average annual temperatures over the year, and you'll see how it's stayed outside the envelope of previous years for most of the first 6 months of this year. And we're seeing an impact of all this on extreme weather events. And this is actually something I want to talk about a little bit more, because I think it's one of the more challenging aspects of understanding climate change, is making this link between the global changes driven by greenhouse gases and extreme weather, because it's these extreme weather events that actually cause harm. And what you're seeing here is the Intergovernmental Panel on Climate Change's assessment of both how extreme weather has changed, that's the colour, and these are extreme heat events here. By the way, defined as not particularly extreme, so just, the definition, obviously, there's an element of subjectivity in what you decide is an extreme weather event, and an extreme IT event. Hopefully that's not too extreme. Thank you. And so, again, if we look at the Sahara and the Arabian Peninsula, you can see that they're coloured red, meaning there's been an increase in the incidence of high temperature events. And the two dots mean we've got a medium level of confidence that this increase that we've seen is attributable to human influence, the increase in greenhouse gases. There's only a few regions, there's further north, but basically a large region of Eurasia where we're pretty confident that the increase in high temperature events is clearly linked to increasing greenhouse gases. Very different picture when it comes to heavy precipitation. There was those floods that happened in Dubai just a few weeks ago. Of course, there was an immediate discussion, is this climate change? Well, the answer given by the IPCC in this latest assessment is we have to be honest about this, we don't know. There's not much signal here, that's why it's grey, and there's actually rather limited data on what's happening to extreme precipitation in this region. And you can also see how there's no confidence that there's any attributable change. But that doesn't mean, of course, that it's not happening. Absence of evidence isn't necessarily evidence of absence. And indeed, that's one of the really important debates we've had in the IPCC about presenting this kind of information. And this was certainly a big issue, I know, in the fifth assessment report. You'll notice Africa is largely grey with white dots here, because of limited data and limited understanding and limited ability to model African weather. We can't say very much about what's happening to extreme rainfall in Africa, but that doesn't mean that nothing's happening. And so it's quite a challenge here to sort of differentiate what we don't know because we just don't know, and what we don't know because the signal's small, and that's actually one of the big debates. One of the things you'll see here is that the confidence we have in linking extreme weather events to climate change is a bit of a respecter of not geography, but who spent the money on the modelling, and that's a problem. We've got increasingly now in the UNFCCC discussions the issue of adaptation, and of course loss and damage is becoming more and more to the front of the conversations, and if the only parts of the world are the ones where you can actually say what the impact of climate change on weather are the ones that have been making the investments in weather models for decades, it's another injustice coming into the whole system. And that's actually one of the points that Tim was very keen for me to make, is we need to, as it were, sort of, well, I don't know, this is my way of framing it. He probably wouldn't have used these words, but we almost need to decolonize climate modeling. In that it's emerged from the usual suspects, and the models we use have been developed for and tuned to mid-latitude weather because that's what they were for, and they're not very good in the tropics, and for various reasons I'll come into actually in the course of the talk. And so if we're going to answer these questions about what is happening to tropical weather, what is happening to, we need a real step change in our ability to model it. Droughts, just as important as extreme rainfall, in many regions of the world more so. Again, a similar picture. You can see there's lots of single dots, meaning low agreement, low evidence. Even though there are signals emerging in some very, very important parts of the world, like West Africa, Central Africa, there's evidence that there is an increase in observed drought, but we're not quite sure why, and therefore we're very confident in projections of what's going to happen next. Again, all this I'm stressing, this is what we're observing. This is what's happening as opposed to projections of the future. And we've done a lot of work, actually in Oxford and other places, on this whole challenge of linking climate change and extreme weather events. It's one of the key asks that's being made of climate physics at the moment. People want to know the answer, and there's a lot of interest in the whole question of what is the link between rising greenhouse gases and extreme weather events. But it presents really quite serious challenges. And I'm going to talk a little bit about one approach we've taken, actually some work with Tim, on how we address this question with a model that, well, unlike most of the world's climate models, is close to passing what Tim calls the model Turing test. So this is an image. So one of these images is a satellite image. The other is from a weather model, and the sort of game is you have to try and tell which is which. Well, I won't push you on that. But the point is, you hesitate a little bit. I mean, if you look carefully, if you're into this sort of thing, you can spot differences. But, from a distance, if you fuzz your eyes a bit, this is pretty close to passing as it were, the Turing test. At this scale, you can't tell the difference. And what these are, of course, the left is the weather satellite, and the right is the European Centre's integrated forecasting system model at the end of a 3.5-day forecast. We're going to use this model now and show you how you can, and one of the things that Tim and I feel very strongly about is that we've got these tools that we use every day for weather forecasting. They're tested relentlessly because every time the weather forecast goes wrong, there's a sort of, great navel-gazing exercise in the forecasting center as to why on earth it went wrong. And yet we don't really use them for climate, which is odd, because they're sitting there as a resource, and we should be. So here's an example of a study that we've got submitted at the moment, looking at a recent notorious extreme temperature event, the 2021 Pacific Northwest heat wave, which did a huge amount of damage and was associated with a lot of wildfires in that region of the world. And it was also, meteorologically, it was a very, very interesting event. I mean, if you look at that time series of high temperatures since 1960 in the corner there, you'll see how what happened in 2021 was, it was a 4 sigma event. So to use the distribution of past events to try and make a statement about that event is really stretching credibility, because clearly something happened in June of 2021 which simply hadn't happened before. It wasn't as if it was, a little bit bigger than the last big one. It was just something qualitatively different. What was interesting about it was that it was extremely well forecast. And, 2 weeks ahead, this was the forecast from the European Centre's medium-range forecasting system. You can see, the lines are isolines of pressure, so they correctly forecast the anticyclone, the high-pressure event, and the surface temperatures, including these totally unprecedented surface temperatures. Of course, the fact that it was forecast was very, very important for the consequences of the event, so people did have warning, and so that the forecasting centres did a good job there. But, of course, that didn't stop the impacts, but it meant that at least people were able to prepare for them a little bit. Even 2 months out, apologies for 59 days, technically it was 59 days, but forget about that, it's just 2 months, thinking at the, and this is not a forecast of the temperatures on a particular day, but just in a seasonal forecast, the hottest day of the hottest 3-day period of that forecast, and showed that, with the conditions that were extant in the Pacific Northwest and Pacific at the beginning of this season, it was possible to forecast. There was a possibility of seeing an event of this magnitude. So I'm showing you this because, unquestionably, I think if you can forecast it, it means you can model it. I mean, or that you got really lucky, I guess. But the point is, if it's something completely unprecedented and the model forecasts it, you have to get, well, I guess you have to get really, really, really lucky. I mean, 4 sigma lucky to actually do that by mistake. This is clear evidence that the model is actually capable of simulating the event in question. And, okay, so what we did was an experiment, which I'll take you through, to look at the impact of external drivers of climate on this event. And it's a very simple experiment in design, quite a complicated experiment to execute, but essentially the idea is you take the forecast that was actually made by the Weather Forecasting Centre, you modify both the initial conditions and the concentrations of CO2 in the model, and then just rerun the forecast to see what happens. So model it, and we modified them in 2 directions. One, to sort of simulate a 1900 sort of conditions, so pre-industrial, if you like, climate, and the other ahead in time to a sort of late 21st century situation where the world's a bit warmer and CO2 concentrations are a little bit higher. And that's sort of blue is this pre-industrial climate, red the post, well, no, I wouldn't say post-industrial, but future climate. And just to illustrate the point with a simpler system, this is the Lorentz 1963 idealized atmospheric climate model of chaos. And imagine, it's a variation on that, which actually Tim suggested a while ago, where you've got an external forcing pushing, sort of like a wind blowing on the Lorentz butterfly in the XY plane. And so you launch the forecast. So these are the forecast initial conditions. And then in one case you have an external driver, in the other you don't. So those are the 2 colors you see. Some of them are driven, some of them are not. And you can see how they diverge, but they all head off in roughly the same direction. But you can see the impact of the external driving on these, and that varies. You see heat waves. If you imagine a high X event is a heat wave, you see heat waves in both ensembles, but there's a few more heat waves in the blue ensemble than the yellow one. Yeah, just for an illustration here. And this technique allows you to look at the impact of the external forcing on the probability of an extreme event happening. So what happens in the European Centre model? Well, remember, blue is the pre-industrial climate, red is the future climate, and you can see there is a clear, can I point to it? No, you can see what the dotted line over on the right there is what actually happened in reality, and you can see that the red distribution is displaced upwards, and there is an increase in the proportion of the red distribution that is above the line, so we can say there's a roughly 8-fold increase in the probability of occurrence of that event as a result of the increase in greenhouse gases and the warming that's happened since pre-industrial. We can also say Another way of, thinking about the implications of this information is that the probability of occurrence of that northwest heat wave, of an event like it, is doubling every 17 years or so. I think that was the central estimate that Nick came up with. So that's the speed with which the probability is increasing. What we can't say is what the absolute probability is, because we're not yet able, we don't have the computing resources to run this model or model of this caliber indefinitely to look at the statistics of these extremely rare events. But, drum roll, the next step is the EVE project, Exascale Virtual Earth, and this is a project that Tim Palmer has been developing with Bjorn Stevens at Max Planck Institute and others, and it's, they would argue, sort of the next big challenge, I would agree with them, is the next big challenge for climate modeling is to actually bring the power of exascale computing to this challenge of understanding the relationship between the big drivers of climate change and extreme weather in particular. I think it's fair to say that there's a bit of a danger in, certainly in the COP, in people thinking, well, we kind of understand what's happening to global temperature. And it's true, we do understand what's happening to global temperature. Certainly on the, we're putting every ton of carbon dioxide we put in the atmosphere dries up global temperature by another 0.5 trillionth of a degree. And, what more is there to say? As far as what to do about carbon dioxide is concerned, there's not much more to say. Yeah, we know what to do. We've got to stop putting carbon dioxide in the atmosphere. But to understand the impacts and to adapt to the impacts and to address issues like loss and damage, we obviously need to have a much more detailed and much more robust understanding of what the relationship is to what's happening on a global scale and our regional weather. And at the heart of this is the challenge of turbulence, if you like, which is long an established sort of one of the archetypal problems of physics and engineering. And this is, if you look in observed weather, observed atmospheric data. So on in the big panel here, you can see for wind, zonal wind and meridional wind, so the different components of the wind, looking as a function of scale, wavelength in the horizontal, and power in the vertical, spectral density more specifically. You can see there's this continuous relationship, the suggestive straight lines have been plotted through it to argue that it's, minus 5.3 power law over much of it, and then minus 3 power law over the larger scales. And that minus 5/3 power law is what you would expect from turbulent fluid, with the scales of the atmosphere, both in the vertical and the horizontal. And the crucial point about this is it's continuous. There's no break there. There's no possibility really of separating this flow into a large scale and a small scale. Every scale is working here, is feeding in to the events we're seeing. So, as in any turbulent fluid, there's power on all scales and they all interact, both upwards and downwards. And the problem is that when we model this in conventional climate models, we have to make a scale separation, which we typically do at a scale of around 100 kilometers, or some of the better models, maybe 50 kilometers. And above that scale, and we are representing the Navier-Stokes equations explicitly, and with a dynamical, either spectral solver or grid point solver, and so we divide the world up into a grid and solve the equations like sort of usual Lego setup. But on smaller scales, of course, we just have to resort to parameterizations. We have to say, well, there is this relationship between the conditions in this grid box and our expected cloud cover, for example, and then that feeds back into the large scale But these parameterizations, although they're based on lots of observations and physical understanding of what's going on, they're not an actual representation of what's going on at those scales. It's just it's an expression of the large-scale consequences of what's going on at those small scales. And there are actual physical processes that just risk being left out altogether. Deep convective clouds, look at all the structure in that amazing picture of lightning in a deep convective cloud. That would all be within one of these Lego blocks in a complex climate model. So none of that structure and behavior would appear. Orographic drag, likewise. We have the mountains in a climate resolution model are inevitably smoothed out, and so you have to artificially add sort of viscosity to the model near the surface to sort of replicate the impact of a rough surface. That's not exactly how they do it, but it's sort of, you kind of have to fudge it a bit. You can tell that I'm not actually a demonstrate dynamicist here, but Tim would say this much better. Sorry, Tim, he's probably looking at the recording and so embarrassing myself here. But the processes we're dealing with here are intrinsically small scale. And of course, in the oceans, it's even more extreme because of the Rossby radius in the oceans, because of the greater density of water and the stratification of the oceans. The Rossby radius is much, much smaller than the atmosphere, so you have an even greater prevalence of small scales that we just don't represent at all, don't reproduce at all in our climate models. So, and of course, the Earth's surface itself is very complicated, and dealing with that is a challenge itself. Why does this matter? Well, at the very large scale, just saying how much the world is going to warm in the future, the notorious climate sensitivity problem, is acutely sensitive to what happens to clouds. If we have more cirrus cloud, more high-altitude cloud results in a warmer surface, because cirrus cloud acts as almost like a greenhouse gas, if you like. More stratus cloud, that's low reflective cloud, that has the opposite effect. It cools the surface. And as we act on, one of the really interesting phenomena that's happening at the moment, we may have seen, I think it's, I'm about to say something which goes beyond, I think, there's been a lot of discussion about whether global warming is accelerating at the moment. I think, to be fair, the evidence is not yet clear whether we've seen acceleration in global warming over the past decade. It's just, the record is just too short to be able to say that on the basis of what's happening in the real world. Plenty of people are saying it. The data is certainly consistent with the warming having accelerated in the past decade. And there's also plenty of reasons to think that it might have done. Methane emissions have gone up, for one, but also, crucially, countries are claiming they've started to clean up air pollution in cities, which, like low-level stratus cloud, helps keep the planet a little bit cooler than it would be otherwise. Now, it's a good thing that this pollution is being cleaned up because it kills people, and I'm not suggesting that this pollution is a good thing, but one of the side effects of a rapid cleanup of our troposphere reveals a little bit of the warming that was already there from greenhouse gases. So understanding that process, understanding that acceleration is really important. It's very topical at the moment. Looking further ahead, the sort of key uncertainty in the projections of these models is in long-term precipitation changes. And I'm showing you this, Tim suggested I should show you this figure, because this is from the latest Intergovernmental Panel on Climate Change report. It's projected precipitation changes. You don't need to notice anything except the diagonal lines which show you where there's no robust significant change. Doesn't mean there's no change. The colours indicate there's all sorts of changes are predicted, but we've got no confidence in them. And look at those maps. There's diagonal lines all over the place. There's even some areas where you can see double hatching, sort of crossed lines, and that means the models don't even agree with each other at all, never mind there not being significant. So it's kind of all over the place, and this is a really important, arguably even more important than temperature, variable for us to understand how it's evolving. So we need to work on it, and this is why we need this sort of next step change in computing capacity. We're also more dependent on weather, as we rely increasingly on wind and sun for our energy. We're actually, we need to have advance notice of periods of energy drought or renewable energy drought in regions where we're reliant. So events like, say, in 2021, when we had a very still period and all the wind turbines of Europe suddenly weren't generating anymore. And of course, if we're talking about adaptation to climate change, we need to know what we're adapting to. In a region, are you adapting to more floods? Are you adapting to more droughts? What? So what we need is, I think, a lot of people in the scientific community agree, and it's something maybe Institute of Physics has also gotten involved in terms of the discussions around this, is an effort to draw countries together for an international effort, like a CERN for climate change, the way Tim put it, where we get an international effort to gather together countries to really push the boundaries of what can be done in climate models in order to build these digital twin Earths, in order to actually address these questions objectively. Because, at the end of the day, people are being asked to do something about climate change. So I always like to remind people, if you're being asked to do something about climate change, you deserve to know what climate change is doing to you. And we can't answer that question for many people in the world because we just don't know, because the things that affect them are extreme weather events. And in many parts of the world, we just don't know how extreme weather is being affected by climate change. How am I doing for time? Who's keeping track of it? Because I didn't really track. Can I give me? Okay. So because that was a reasonable punchline. So I didn't remember that punchline, and I'll just sort of. So okay. I was going to talk a bit about because I've been talking a lot about the uncertainties in modelling and so on. I just wanted to remind you that there is a lot we can say, or there are some things we can say about the cost of climate change. I don't want to send the message that this is all hopelessly uncertain. Lots of models of how warming temperatures affect the global economy have more or less the same shape, and I'm showing you a couple of them here, but I could show you many. They all have more or less this sort of quadratic shape as they move away from pre-industrial temperatures. We see not only increasing costs, but an increasing rate at which costs increase. And that's really the sort of simplest possible model or understanding of how climate change can affect the economy, because we're moving away from the climate with which economies have grown and adapted, and ecosystems and societies have grown and adapted to them. And because we also know that global cooling is at least as damaging as global warming, so we should expect this quadratic shape to apply on both sides of the zero line, which is why we know it has to be pretty much this shape. So we can argue till the cows come home about exactly what the vertical axis is here, whether 3 degrees of warming costs 2% of the world economy or 4% or whatever. And this is where there's a lot we can't say about the cost of climate change, not just because we're not very good at modelling the impact of climate change on extreme weather. That's one important element of what we don't know. But also because, you have arguments about things like the statistical value of life. How do you assign an economic value to impacts on different people's lives in different parts of the world? And these are really fundamental philosophical arguments that you can't really, even with Tim's digital twin Earth, you're not going to solve that one. Risks like mass movements of people being triggered by climate change and so on, these have sort of non-economic consequences. So, none of this allows us, there's great uncertainty in exactly what the costs are for different levels of warming, but we do know that it's that general shape, and that therefore, a warming of 1 degree costs $D billion of damage. I don't know what D is, But it doesn't matter in the sense that I know that at 2 degrees, it's going to be 4D, okay, at least 4D, because we're going up in that quadratic shape. And that means at 1.5 degrees, it's 2.25D, again, not complicated sums. And at 1.25, which is where we're at the moment, it's 1.6D. So one thing you'll notice straight away is the difference between 1.5 and 2 degrees is at least as high as the damage caused by climate change to date. So whatever that is, we can argue forever as to how much it is, the difference between 1.5 and 2 degrees is the same again. And that's why, despite what I've told you about the uncertainties and the relationship between climate change and extreme weather and so on, one thing we can be pretty confident about is going from 1.5 to 2 degrees is going to be as harmful, at least as harmful, as all of the climate change, all of the impacts of climate change to date, up until the present. So, there's a reason we're all spending time down in Doha, just to remind yourself, there's a lot at stake here. If we have to settle for 2 degrees instead of keeping temperatures closer to 1.5, we will lose a lot. I mean, this is what we've resolved to do, limit it to well below 2 degrees, aiming to limit the temperature increase to 1.5 degrees. It's a rather vaguely worded challenge in the Paris Agreement, but what it really boils down to is Paris agreed, okay, given we're at 1.25 degrees now, we're warming at 1/4 degree per decade, Paris agreed to stop global warming within a generation. Either 20 years if we're going to limit warming to 1.5 degrees, or around 50 years if we're going to limit warming to less than 2 degrees. So that's the time scale on which we have to stop global warming if we're actually going to deliver the goals of the Paris Climate Agreement, whether it's 1.5 or 2 degrees. That's the speed with which we have to turn this thing around. And what does that mean? What does it involve? Well, it's pretty simple. These are the scenarios that limit warming to 1.5 degrees, but the 2 degree ones look pretty similar. What you're seeing here in red is the amount of carbon dioxide we still produce from burning fossil fuels in these scenarios. And you'll notice that does go down dramatically as soon as you start to apply climate policy. But you'll also notice it doesn't go remotely close to zero. We're still using fossil fuels beyond 2100. And, the reason we actually managed to stop global warming in these scenarios is because of the blue curve, which represents the rate at which we're putting carbon dioxide generated by burning fossil fuels back underground. Carbon dioxide either captured at source when it's generated or recaptured from the atmosphere and re-injected into the Earth's surface. And that's the balance between the red line and the blue line is the point where we stop fossil fuels from causing further global warming. We'll see that, therefore, stopping climate change is a combination of burning less and storing more. This is capturing carbon dioxide, injecting it at least a kilometre down, sometimes up to 2 kilometres down into the Earth's crust, into the same kind of geological formations that we find hydrocarbons in the first place. And if you inject it there, it diffuses into the rock, and it ends up stuck to the rock. And it's actually impossible to get it back out again. You can have a percentage may leak, but the vast majority of it stays there. Catherine Romanek compares trying to get the CO2 back out of rock to, trying to get the mayonnaise back off. If you spread mayonnaise on a slice of bread and then you try and scrape it off again, you're never going to get it all back. There is, of course, an important contribution from nature-based solutions, and there's a lot of conversation about nature-based solutions at COP. The fact that we're currently allowing carbon out of our biosphere into the atmosphere by deforestation. We need to, stop deforestation and start to restore the biosphere. But the important point about that green curve is, compared to the other curves, it's an order of magnitude smaller. So there's a lot of talk, again, at COP about sort of, quotes, abating fossil fuel use by nature-based solutions. Well, on a global scale, that's not going to do it. They may be very useful, they may have all sorts of other benefits, but they're not the answer to continued fossil fuel use. We have to get, to stop fossil fuels from causing global warming, we have to get to what we call geological net zero, where you're putting CO2 back into the Earth's crust at the same rate that you're putting it out. And, getting there is going to be challenging because at the moment it's much cheaper to reduce emissions by not producing CO2, that's the red line, than it is to reduce emissions by storing CO2 either at the surface or back into the Earth's crust. But eventually, when we get to about sort of 75% or so of our current emissions eliminated, that final 25% are activities like cement production, like aviation, where it's just, there are no substitutes for the use of fossil fuels or the generation of fossil origin CO2. And that's where stopping those emissions becomes horrendously expensive. And that's where carbon dioxide capture and storage comes into its own. But the problem is, if we leave it until we get only to those, if we've already reduced emissions by 75% and then we start to think about it, that's where we've run out of time, because it's going to take us a while to develop this technology and prove it can work to the public. I mean, some people do get this. Sultan Al-Jaber has insisted, and he's been criticized for doing so, but I think he's quite right, that we need to be laser-focused on scaling up, laser-focused on phasing out fossil fuel emissions and scaling up viable, affordable alternatives. And he was criticized for saying this, and still is being criticized for saying this, by the likes of Christina Figueres, saying, well, it's not just about emissions, we don't have it commercially available, it's just not going to happen. CCS, she's talking here, is carbon capture and storage, this process of capturing CO2 and putting it back underground. I mean, I think there's a lot of debate. I just sort of share with you the conversations that are going on at COP. There's a lot of debates at COP about, should the COP be saying we're going to phase out fossil fuels? A lot of people are insisting that if it doesn't say that, it's a failure. The sort of compromise language that some people are talking about is phase out of unabated fossil fuels. I personally hate this idea because I have no idea what unabated fossil fuels means. It can mean anything. And, what do we mean by partially abated fossil fuels? Are they okay? Well, the answer is they're not. So what am I to say? But if I was asked, I would say we should really, it'd be much better to adopt a positive framing and say we should be scaling up technologies to capture and dispose of carbon dioxide such that any ongoing fossil fuel use is fully abated in time to reach the goals of the Paris Climate Agreement. I mean, I understand what fully abated fossil fuel use means. It means you're not putting any CO2 into the atmosphere. I don't really know what unabated fossil fuels means. So I think if we talk about it in a positive way, we're more likely to make some progress, or at least we're more likely to end up with something that means something. Maybe that's a reason not to do it, because for some people, slightly too meaningful outcomes are not what's wanted. But anyway, there we are. And just to reassure you, to end on a positive note, because everybody's sort of feeling a downbeat about this, there were some really interesting developments at COP, and one of them was little heralded, hasn't been much noticed, is something called the Carbon Management Challenge, which was launched, it was floated by President Biden earlier this year and was formally launched at COP. And this is a coalition of countries, including UAE and Saudi Arabia, with a stated goal of putting 1 billion tons of carbon dioxide per year back into the Earth's crust by 2030. And, if we manage to reduce emissions at the same time by not 50%, but, a modest or so 15-20%, then that 1 billion tons would constitute 3.5% of our ongoing production of carbon dioxide in 2030. And if you think of this in terms of the rate of acceleration in that stored fraction between now and then, that means an acceleration rate of 0.2% per year. It's an acceleration, so hence per year. And if we kept our foot on the carbon storage accelerator at that rate for 25 years, we hit 100%. What happens? We've stopped global warming. So if they can keep up that rate of acceleration that they're promising under the Carbon Management Challenge, it will inevitably mean fossil fuels getting more expensive and us using less of them, but it'll mean also building a huge global industry of carbon dioxide disposal, and they've got to get on with it, that we will actually stop fossil fuels from causing global warming and not too far off the time required to meet the goals of the Paris Agreement. So, let's celebrate the fact that there's progress being made. This wasn't being talked about even 2 years ago. So, on that positive note, I want to wrap up. Just to stress, we need to stop fossil fuels from causing global warming, and we need to do it before the world stops using fossil fuels. If we'd have started trying 15 years ago, maybe we could have met our climate goals by just stopping using fossil fuels altogether, but it's too late now. We've got to actually do both. We've got to both scale up permanent disposal of CO2 and scale down the rate at which we use fossil fuels at the same time. As Sheikh Yamani once put it, the Stone Age didn't end because we ran out of stones, the oil age won't end because we run out of oil, and global warming must end before we stop using fossil fuels. So, on that note, maybe you've got some comments.
Thank you. Fantastic talk, Miles. Eloquent, clear, to the point, honest about what the world faces, in your opinion. Let's hear what other people think. Any questions? Yes. Paul, come.
Yeah. Thanks, Miles. It's always bugged me, this about the agreement and warming well below 2 degrees. I've no idea what well below 2 degrees means. Perhaps it's clearer to other people. I mean, to a mathematician, it means an order of magnitude less than 2 degrees. So is there a consensus about what well under 2 degrees actually means? Does 1.9 degrees count?
Yeah, I mean... Maybe I need to ask for my thing. It's gone green. Should we try the other one? And that is working. Yeah, okay, great. Yeah, I mean, to be fair, I think the negotiators should be given some credit for the fact that, I mean, obviously it's higher than 1.5 because they also set the goal of pursuing efforts to 1.5, so it's recognized that it's somewhere in that vicinity, I think the precision with which you can make any statement about global temperature indicates well below has to mean. I mean, a difference of a few centikelvin is not a difference. So it's sort of several tenths of a degree below 2 degrees, and therefore I think most people interpret it as sort of somewhere in the middle. I think if you want to get more precise than that, then you're dancing on the head of a pin because, what's the point? So, I mean, people are saying 1.8 and, they're sort of, but as far as I'm concerned, somewhere in the middle.
Let me ask you a question, Miles. So you talked about the transformation that's required with to stop global warming before we stop using fossil fuels, and CCS has to be implemented at scale and at pace. And you talked about the new plan, what was it called again?
The Carbon Management Challenge that they've just launched. Yeah. It's not exactly a plan; it's more an aspiration. I mean, that's.
Well, this is where I'm slightly confused because the scale of the problem and the scale of the storage requirements is phenomenal for the volume of CO2 that has to be captured, transported, shipped in many cases from where it's being generated to where it's going to be stored, and who's going to pay for all of that. The capture is only one part of the story. And then the reservoirs and the trust and verification schemes that need to be put in place. I mean, realistically,
I'm absolutely confident it could be done, and I know who could do it, and that's the fossil fuel industry. And they understand the subsurface very well. They understand all of the problems that you described, moving dangerous fluids around in pipes, Yes, they've got a checkered history, but at the end of the day, they are over 10% of the world economy, and they move an awful lot of pretty dangerous stuff around the world, and they don't tend to have accidents, touch wood, that often. I mean, so, yeah, they're absolutely capable of doing it. And we've got to realize they can also do it at speed as well, in that they've done things quite similar in the past. If you think about the mid-2000s, nobody heard of hydraulic fracking, and it transformed the global energy economy and converted the US from a, a dying energy power into the world's leading energy supplier in less than a decade. So, when the industry, and of course it did it because the oil price was driving it and everybody wanted to make money. So if you manage to engineer the policies such that there was money to be made in getting rid of CO2, rather than just a subsidy to be had from the government, then it could happen very fast. But the problem is, at the moment, we don't have those policies in place. So the only way you get people to do CCS is the government pays for it. And then you've got a long-winded negotiation. In Britain, we've had sort of embarrassing 20 years of on again, off again, on again, off again arguments about doing CCS. And we seem to be doing it at the moment, but we're still doing it because the government is paying for it. We're not there's no business case for it per se. So one of the things I'm perennially going on about is that essentially this is not going to happen until it's a licensing condition of getting fossil fuels out of the ground. If you want to pick it up, you've got to put it back. And if that was the condition, I firmly believe the industry would just do it. And they'd crack on, and they'd do it surprisingly quickly. Because if the alternative was them not making money, you'd be amazed at how ingenious these people can be.
I think we all agree on that. Okay, so now your question back. So what would it take to make that happen?
Well, a bit of gumption on the part of governments, I'm afraid. And again, one of the things that frustrates me about COP28 is all the conversations about, how companies need to be more virtuous from and politicians nagging companies for behaving badly. Well, if a company makes money in a way that you don't like, well, change the rules. I mean, you make the rules. And this is, I think at the moment, there's a lot of governments at COP28 kind of hiding behind this myth of an evil industry to get out of their responsibilities. They need to regulate it. They need to step up.
Which comes back to some of the discussions and conclusions from panel one about the lack of political leadership.
Yeah, I mean, we've got a leadership back. We've also allowed this problem, and the academia. I think we need to look at ourselves as well. I think academia have allowed this to become way too complicated. The arguments at COP are, they're so, and not just academia, but the sort of academia industry interface that is consultancy. I mean, they love making it complicated, So the panels about carbon markets and credits and so on that are going on at COP, I mean, you walk in and you've no idea what's going on. And, at the end of the day, stopping fossil fuels from causing global warming is pretty simple. Don't put the CO2 into the atmosphere. If a country wants to stop global warming or wants to stop contributing to global warming, they've got to pass a one-line bill. After 2050, you can't sell stuff that causes global warming. I mean, that's how we fix the ozone layer.
Any final question? If not, let's thank our speaker.
Great, thank you. And as a fellow of the Institute of Physics and a member for about 25 years, I think, since my student days, it's a great pleasure for me to be able to chair this final discussion session today on sustainable transport. And I guess the key challenge facing the transport system is, of course, the fact that getting something from A to B requires movement, and movement requires kinetic energy, and we've got to get that energy from somewhere. And moving a big thing requires a lot of kinetic energy, and cars and trains and planes and ships are all big things. So lots of energy involved, and of course historically fossil fuels have been the only way of getting that energy. Nevertheless, I remain quite optimistic, I have to say. I think there are plausible realistic pathways to net zero or even true zero for the transportation sectors by 2050, and I'll show you that evidence shortly. Maybe I'm slightly naive, but I'm kind of optimistic that we'll make it. So this is going to be a real treat for me, this session. We're going to talk about aviation, shipping, and ground transport, and the prospect of making all of these sectors sustainable. Right, so moving straight on, I'm going to talk about aviation specifically. And just as an example, really, of a pathway to, actually not net zero here, but true zero. So there's no offsetting involved here. This is a pathway by which aviation could reach true zero by 2050. From a report that came out actually at COP27, so it's almost exactly 1 year ago, we're looking at annual emissions from the aviation sector going back to 2019. So we've got 4 years or 3 years, I guess, when the report came out of real data, COVID dip, of course, and a bounce back. And then a scenario for going forward to 2050 with obviously some growth, a lot of growth in the sector, as you can see there, which, of course, if emissions tracked that top curve, that would be completely unacceptable. So what this report does is it looks at breaking down how we can take slices away from that curve through different interventions, pulling different levers. Don't know if, it does work. So for example, in the color scheme here shows you what the levers mean. So for example, flight operations, improvements to flight operations, calculating flight routes such that they minimize fuel burn rather than economic cost, which is what's currently minimized. Shaves a little sliver off, not very much. Air traffic control improvements shaves off a bigger slice. There's some crazy behavior today where some countries charge a lot to fly through their airspace. And so a flight route that would go through that airspace, the airline will say, well, we're not doing that, and they'll fly around it. And of course, it costs more in terms of fuel consumption, but not as much as they would have to pay to fly through the airspace. So there's cost saving, but it comes at an environmental cost. And by doing away with these air traffic control absurdities, frankly, there's potential to shave some more off. Contrail avoidance, so this is carbon dioxide equivalent. Contrails also have a warming effect, nothing to do with CO2. So these are the condensation trails, the lines you sometimes see in the sky behind a plane, which have a warming effect. And in fact, there's discussions going on at COP this week that we in fact already have today the technology and the know-how to avoid forming contrails. The military already do that and are very good at it. It's just civilian aircraft that don't have that know-how. But there are companies here at COP. Satavia is a tech startup in the UK, which has demonstrated quite convincingly, I think, that we know how to avoid contrails, and we could be doing it today, but we're just not incentivized to, because the CORSIA, which is the International Agreement on Aviation CO2 reductions, is all about the CO2 and not about the non-CO2. And then we go on to next generation aircraft, so hydrogen-powered aircraft, for example, new fuels, etc. Can all shave parts off this curve and get us down to about an 85 to 90% reduction compared to the baseline, with a little bit of residual emissions that we would need to remove from the atmosphere. I would like to stress, though, that this is not a fringe report by people who don't know what they're talking about. This is by some real professionals, Roland-Berger, who know their stuff, and consulted widely with academics and scientists and industry specialists in putting together this report. So I really do think this is a plausible way, one of many plausible ways, that aviation could become true zero. There's no offsetting here. It's not net zero, it's true zero by 2050. So I think there are grounds for optimism. And I'll talk you through the evidence for some of those grounds. This was a paper we, in fact, published in an IOP journal, in Environmental Research Letters, one of the flagship IOPP journals, and it was a PhD student of mine, Kathy Wells, who compared actual flight routes across the Atlantic with her calculated best possible routes that minimize the fuel burn. So every day we looked at actual flight routes across the Atlantic. She calculated the best possible flight route that would have minimized the fuel burn, and we compared those routes and found, as you can see, or perhaps you can't see, it's quite small, but a typical transatlantic flight is hundreds of kilometers longer than it needs to be because of these prescribed track. There's a track system across the North Atlantic. And so we calculated that you can save up to 7.8% of fuel on a westbound flight, up to 16.4% on an eastbound flight, by allowing aircraft to fly along the most efficient route. And this is a change we could make today. Don't have to wait decades for technological improvements. It's a change we could make today. And happily, it's a change that is happening. A week after we published that paper, the UK's air traffic controllers, NATS, announced an experiment where they would abolish the prescribed tracks that aircraft had to fly along, at least up to a certain altitude. And in fact, that experiment was successful, and those tracks have now been permanently abolished up to a certain altitude. And I think that's going to lead to a real saving in transatlantic aircraft emissions, starting now, essentially. It's just a few percent, but I think we'll take a few percent. I think we take everything we can get. And the next speaker may dispute this, but I did come across this paper that came out recently, which suggests that there may be similar strategies that we could use in a maritime context. I know very little about this, but the claim here is that wind propulsion is a retrofit option where sails provide renewable power. And combined with voyage optimization, and we have another extreme event, and reduced shipping speeds as well. Thanks, Alora. The claim in this admittedly academic study is that we could reduce carbon by up to 60%, it says in the abstract, for shipping. Now, we were asked to talk about misconceptions, so here's my big misconception. I think it's a myth. I think there's a lot of, in fact, all of COP is about mitigation, quite rightly, but I think we do need to adapt as well to climate change. We need to adapt our transportation infrastructure to the impacts of climate change. It's not enough to mitigate. I think I would argue that transportation is going to be a victim of climate change as well as a cause. And that's because of something called partly because of something called the committed warming, which is the future warming that is going to result from CO2 already emitted, but it hasn't happened yet because there's a delay in the system. It takes the climate system decades to warm. So even if we stopped emitting today, it would continue to warm for decades, if not a century or more. We've already seen a warming of over 1 degree, and there's thinking that there's already a further degree baked into the system because of emissions we've already put into the atmosphere, and there's nothing we can do practically yet to take them out. So I'm going to argue that it's not enough to mitigate, to try and cut out carbon emissions. We should be doing that, of course, but at the same time, in parallel, we should be adapting our transportation infrastructure to cope with the consequences of climate change. So as well as protecting, this is a bit of a soundbite, headline really, headliney soundbite thing, as well as protecting the climate from transportation, we should also be protecting transportation from the environment and climate change. My big fear is not that we will fail to decarbonise or fail to reach net zero by 2050. My big fear is that we will decarbonise, but that we will have forgotten to adapt our transport systems to cope with the climate change that is going to happen whether we decarbonise or not. It's already baked into the system to a large extent. So I'd like to think about the relationship between transportation and the environment and climate as being a two-way problem, a genuinely coupled problem, a two-way street, with each affecting the other. And on the aviation side, there was World Meteorological Organization document published as a result of a conference a few years ago, which made a very sobering statement, really, that using that basically climate change may render some of today's aerodrome, airspace and airframe design and operation standards inadequate in the years or decades to come. Using the past as a guide to the future at an airport may be insufficient. And I'll very quickly go through a couple of possible consequences of climate change for aviation. Sea level rise, flooding coastal airports. And in fact, there's a connection here with ground transport and maritime as well in terms of flooding of ports and roads and rail that are coastally located. It's harder for a plane to take off in hot air. There's less lift generated. So we may see increasing takeoff weight restrictions. Of course, we expect more extreme weather, more lightning strikes en route. The jet stream is, we believe, shifting and maybe becoming more sheared, changing flight routes and fuel consumption, and that increasing shear in the jet stream causing more turbulence as well. So there's a whole plethora of possible impacts of climate change on aviation. And just to dig a little bit deeper, some of you may remember Hurricane Sandy, which went up the east coast of North America and flooded New York. And this is, of course, LaGuardia Airport, which was closed for 3 days. Both the runways were underwater. You can see a jet bridge there going nowhere. I think this is the kind of impact that's baked into the system already, because it takes a long time for the ocean to warm up because of its heat capacity. So if we stop emitting today, the ocean will continue to warm and the sea will continue to rise for a long time. There's a suggestion that events like this used to happen once every 500 years pre-industrially, but today are happening once every 25 years, and by the middle of this century, once every 5 years. So what used to be a twice a millennium event is now 4 times a century, and in a few decades will be twice a decade. Quite horrifying if that projection turns out to be true. And as I mentioned, harder for aircraft to take off. So as for physicists, we all know that the density depends on temperature. As air warms, the air molecules get spaced further apart, so there are fewer molecular collisions with the airframe, and that's what generates the lift. This is a slightly misleading diagram. The molecules don't get bigger. I didn't draw this, I'm not sure, but they do get further apart, and that's the point. And we recently calculated that the maximum takeoff weight, or I should be more precise because we're all physicists, the maximum takeoff mass of an A320 at an airport in Greece over the past 30 years has reduced by 4 tons from 73 tons to 69 tons. So and that's 40 fewer passengers who can be carried at the maximum takeoff weight. So this is something that's already happening and will, of course, continue into the future. Lightning strikes we expect more of in a warmer climate. There's a clear link empirically between lightning and heat. This is, by the way, is a NASA research plane that was deliberately flown through 1,500 storms in the 1980s as an experiment to test what would happen to the... So it was struck by lightning 700 times, and here's one of those times. There's a projection of 12% more lightning per degree Celsius of global warming. Changes to the jet streams. There's a consensus among the IPCC climate models that in the upper atmosphere, the prevailing winds, the jet stream will strengthen by something like 10% on a transatlantic flight, for example. Changing journey times, speeding up eastbound flights, slowing down westbound flights, and indeed the transatlantic subsonic flight time crossing record for an eastbound flight has been broken 3 times in the past 5 years. It was 5 hours and 16 minutes from New York to London, and then 5 hours 13, and now 4 hours and 57 minutes. And I think this is consistent with what we would expect from a jet stream that speeds up. And finally, turbulence. You see anything wrong with that aircraft? Doesn't look quite right, does it? Missing here. So this engine broke off mid-flight because of turbulence. Turbulence broke the engine off. Happens, but it's rare. Causes damage to aircraft, injuries, and has economic costs. And it's going up as well, and it's going up because of climate change. From a study we published a few weeks ago, looking at diagnosing this invisible kind of turbulence called clear air turbulence, going back to 1979 over the US and the North Atlantic. And so this is the probability of encountering severe turbulence. It's quite low. Severe turbulence, by the way, is strong enough to lift you out of your seat if you're not seatbelted. That's the definition of severe turbulence. The root mean squared vertical acceleration of the aircraft exceeds 1g. And there's a clear upward trend. And this has nothing to do with the growth in air traffic. This is an intrinsic measure of the amount of turbulence in the atmosphere. So if you sat for 1,000 hours over the North Atlantic, you get about you would have experienced about 2 hours of severe turbulence in 1979. It wouldn't have been a continuous 2-hour block. It would have been 5 minutes of severe turbulence and then a few days without any, and then another chunk. But that would have increased to about 3 hours by the present day. So a clear increase and a clear link back to climate change. And then looking at the future, by 2065, we expect an acceleration, really, of those increases in turbulence, with hundreds of % more turbulence, severe turbulence, on these busy flight routes within the next few decades. So I think we can achieve a sustainable transport system. There are plausible ways of doing it. There's already low-hanging fruit that we should be grasping with both hands to minimize emissions, to reduce emissions today without waiting decades for sustainable aviation fuel and more modern aircraft. And there's all sorts of interventions that have been proposed to get us there. But I do think the transportation systems need to adapt, not just aviation, but maritime and ground transport as well, with one of the consequences being a lot more turbulence. So that's my little introductory remarks there, focusing on aviation. And next, I'm going to hand you over to someone who knows more about the shipping side of things, to Roel. So Roel, would you like to come up and we'll load up your presentation? You're the head of air pollution and energy efficiency, I believe, at the International Maritime Organization in London. So I'm excited to hear what you have to say about the shipping context.
Thank you very much, and a very good afternoon, everyone. Thanks for the very good introductions and the presentations on, particularly the presentation on the other transport modes. I think there's a lot of similarity, actually, what was just presented between the international aviation sector and the international maritime sector. And I'll try to kind of touch upon those whilst also highlighting the work of IMO. So IMO, the International Maritime Organization, is part of the UN family. So we are actually a specialized agency within the UN system, like ICAO, which was just mentioned. So the International Civil Aviation Organization, which is based in Montreal. We are based in London. So the UK is our host country, but we are an international, a government-driven organization that works on the basis of treaties, and through our treaties we regulate international shipping. What is quite interesting, and I'll just a very quick introduction to IMO and how it functions. Going back actually to the Kyoto Protocol and to the Paris Agreement, international shipping and international aviation were actually outside the immediate remit of the Paris Agreement, meaning that governments, through their contributions, through the national determined contributions, the NDCs, in which they commit to regulate all other sectors, there's no such obligation to regulate international shipping and international aviation for governments. The Paris Agreement, though, made it very clear that for international shipping and international aviation, it's both IMO, so the International Maritime Organization, and the ICAO that have to put in place the international rules and regulations to reduce the carbon emission of those two sectors. And that is quite important to keep in mind. It's particularly looking at shipping, it's unique, or the way shipping is organized makes it very difficult for governments at a national level to undertake anything to reduce emissions. You probably may know that some of the biggest registers in the world, Panama, Liberia, the Marshall Islands, represent the growth of the shipping registry, so where most of the ships are registered. The ownership is in most of the cases completely different. So most of the ships are either owned in the US, China, Japan, or Europe, but not flying a European, American, or Japanese flag. The crew is mostly Filipino, Bangladeshi, Indian. So the whole structure of the shipping industry makes it very difficult for governments at the national level to do something, and therefore it's not included in the Paris Agreement, and the IMO and the ICAO are the responsible UN bodies to regulate and to reduce the carbon footprint. There are about 50,000 ships, merchant ships that operate worldwide which re-regulate IMO. We do that through treaties primarily. So the member states, the governments are the signatories to our treaties. And all the vessels that operate and fly on the flag of those countries then become bound by the treaties to comply with the rules and regulations. When it comes to energy efficiency, we have a main instrument, a convention that covers almost 97% of the world tonnage. So basically the whole fleet is covered by that treaty. And every time that we pass new regulations, requirements through that treaties, a year and a half after governments within the IMO in London agree on those agreements, they enter into force. And they are then enforced globally. So it's quite a unique system. It's for an UN body, the IMO has quite some strength, quite teeth. And that is quite unique compared to other major polluting sectors like steel, like cement, like aluminium, who do not have such a global regulator. So we have quite a big impact on the shipping industry through our rules and regulations. The complex or the challenge in regulating the shipping industry for us is the diverse nature of the industry. I think shipping is even more complex than international aviation. There are much more types of ships than in the aviation sector. Varying from the largest container vessels to oil tankers, gas tankers, offshore container or roll-on, roll-off vehicle carriers, etc., etc. And they operate on the major trade routes, but also in small kind of island regions connecting the Pacific regions with hubs in the regions like Singapore or Australia, in the Caribbean. So all that makes it quite complex to regulate the shipping industry. At the same time, the shipping industry is really the backbone of the global economy. So over 80% of global trade is transported by ship. And what we can see actually now, and as shipping has been, of course, fueling the world economy with oil and gas shipping that around the world, what we actually see now is that there's an increased interest in the shipping industry to become the transport mode to connect the future renewable energy hubs in the world with the large demand, energy demand areas in the world. So and here in COP we're talking about this endlessly, countries in the global south, think about Namibia, Brazil, who are extremely keen on investing in the production of renewable hydrogen, but all that renewable hydrogen needs to be exported to Europe, to the US, to East Asia. And so that is where the shipping industry comes in again as the transport mode to fuel the future low carbon economy. It is, compared to other transport modes, highly energy efficient. Obviously, we do have a relatively large carbon footprint, but compared to aviation, per ton fuel, per mile, or other modes of transport, it is energy efficient. Currently, the shipping industry emits around 3% of global CO2 emissions, and that is equivalent to the aviation sector, more or less. It's also equivalent to an economy like Germany. And so even though it seems relatively small, it's a high number, and we are working on reducing that. We've been doing that for already over 10 years through primarily energy efficiency requirements that consist of quite a comprehensive set of regulations covering the almost entire life cycle of the ship. So there are building or new build standards, energy efficiency standards for ships that come off a yard anywhere in the world through which are regulated through the IMO. And we have quite a recent set of requirements that entered into force actually at the beginning of this year, operational carbon intensity requirements, with the aim to improve the carbon intensity, so the fuel consumed per ton mile, by 40% by 2030 compared to 2008 levels. We also have a mandatory fuel consumption system for ships over 5,000 gross tonnage. So through their flags, through their registers, they report their fuel consumption to us, and we publish that information. For the time being, we don't actually do anything with it, but it is a key element for further future regulations. I'll come back to that in a second, and particularly to monitor the carbon content of the fuel in the future. Our rules and regulations are primarily what we call technology neutral, fuel agnostic. So the IMO does not actually prescribe what kind of technology a ship needs to use or implement. We don't regulate what are the fuels that the shipping industry has to use in the future. Again, because of the high degree of variation of ship types and trades and operational routes, etc., which makes it very difficult for us as a regulator to say what a ship or an operator should do. We just set the target, like for instance the 40% carbon intensity target for 2030, and then it's up for the owner or the operator of the ship to decide what measures it wants to implement. And you touched upon a couple of those. Rotors, wind rotors, are indeed wind assistant technology. It's a very old means of propulsion for the shipping industry, but it's making a massive comeback in a different way. So it's not really sails like they used to be, but they're rotors that are placed on the deck. And depending on the size of the ship, where it operates, it can indeed have an energy efficiency improvement of almost 30%. So that is really, really substantial. In addition, there are many other solutions that are being implemented, trialed right now on the basis of our goal-based regulations. Route optimization is quite an interesting development as well. Similar as in aviation, there are also trade routes, shipping routes that are mapped out for the industry to follow. Weather patterns, though, are also increasingly impacting shipping. So we have to look into that. I don't know if you saw recently, but for instance, the Panama Canal is suffering extreme droughts. And so the water levels in the Panama Canal are the lowest that they ever been. And this has a massive impact on the number of ships that can pass through the canal. And there are waiting times now of up to a month in order for ships to go through the Panama Canal. And so there are many ships that are now actually doing the journey again around the tip of South America, obviously having a massive increase in fuel consumption, but the time is money. So, and that is one of the key things that we see in the shipping industry, that depending again on the ship type, the route that it operates, what kind of charter it is on, speed reduction is one solution. But for container ships operating on highly competitive routes, speed reduction is not really a solution because it will have too much impact on their competitiveness, and they pay more for fuel rather than reducing the speed. Reducing waiting time in ports. So we do see that ships cross the Atlantic on high speed and then wait for 2-3 days at anchor before there's a berth in a port that comes free. So all these things can also be addressed by optimization of ports, logistics operations in ports, etc., etc. Now, last July, the IMO governments, or the member states in the IMO, actually came to a huge agreement in our greenhouse gas strategy, and they came to an agreement to actually reach or to phase out carbon emissions from international shipping around 2050 on a net zero basis. And that is a massive way forward for the shipping industry. If you look at fuel consumption today, which is still over 99% fossil. So having to reduce that between now and 2050 to zero is a huge challenge for the industry. Governments agreed that this transition for the industry needs to be just and equitable, taking into account different national circumstances. This is very much COP UNFCCC language, which also finds its way back into the IMO as a UN body. But it is very important that the shipping industry also serves small island developing countries. It is the main lifeline for exports for many least developed countries in Africa, Latin America, Southeast Asia, that all depend on shipping, the cost of maritime transport services to access global markets. And so the options for the shipping industry to decarbonize and countries not be penalized is something that we need to keep in mind. Governments also agreed last July that the IMO is going to put in place a new set of binding regulations by 2025, and we're working on that right now. That includes a carbon fuel standard, so a global fuel standard for fuels to be supplied to the shipping industry to reduce gradually over time. And that will be implemented with a emission pricing mechanism. And this would be the first global emission pricing mechanism for a global industry. So this is work that is on the way now by us that we're developing. We're carrying out a number of impact assessments and studies to see how that can be implemented in the most effective way without disrupting global trade too much. But it is going to be quite unique if shipping is going to be subject to a carbon pricing mechanism. And that is basically what the shipping or the governments agreed upon last July, the trajectory towards 2050. There are a number of milestones that have been agreed upon as well in order to reach that net zero target by 2050. A high level and a lower level reduction scenario of greenhouse gas emissions with milestones for 2030 and 2040. So 20% greenhouse gas reduction by 2030 towards 70 by 2040, or a 30 to 80% reduction curve to reach net zero. We also, our governments, I have to say, agreed on a target for 2030 of at least 5% of the energy to be used by the shipping industry to be near zero fuel or technology, so a mix of alternative fuels, renewable methanol, hydrogen, renewable ammonia. All these fuels are actually being trialed and tested now in different parts of the world, and there's actually a ship here from Fortescue, the Australian mining company, that has actually a ammonia-driven ship, which they sailed up to Dubai for visitors to get on board. And this is unique for the shipping industry to have an ammonia-driven ship. It's the future, but there are quite a number of challenges that need to be overcome in terms of safety regulations, the training of seafarers that have to be able to safely handle ammonia, and of course access to these renewable fuels for the shipping industry. So these challenges, I think I put them out here on the table and leave it with that for now. Thank you.
Many thanks. Thanks for that very stimulating talk. And we're moving on now to the final speaker, who's going to cover ground transport. So it's Meta Al-Ketbi, and you're haven't come very far, from the Ministry of Energy and Infrastructure here in the UAE. So welcome, and I'll hand the microphone over to you.
Thank you. Thank you all, and I'm glad to be here, and I thank IOP for inviting me to be part of this event. And it's my really pleasure to be part of this, all these speakers here in the room with all their expertise. I'm electrical engineering, and I start my career path with the Ministry of Energy. So I have been working just for now almost 2 years. So you have a lot of good insights starting from today, and I learn a lot from you. So I hope that you also can learn from our project about the green mobility. So I hope that you can enjoy my presentation. and I promise you that it will be short, just 2 slides, because we are reaching at the end of the event, and I believe all of us are exhausted and we are running out of time. I just give you a background first about the National Demand Side Management Program. This program was developed to target the highest energy consumer and water consumer sectors, which are the built environment, agriculture, industry, and transport. We aim to reduce the energy consumption by 40% by 2050, and the water by 50% by 2050. To ensure reaching these targets, we initiate different initiatives under each pillar. One of the main pillars is green mobility. This initiative aims to reduce the consumption in the industrial sector by 40%, which is equal to 4.6 million tons of oil equivalent by 2015. In this program, we collaborate with all the federal and local authorities and organizations here in the UAE, so we'll align all our efforts to reaching our target. The program, if we are talking away from the green mobility, we are trying also to improve our fuel efficiency by setting a standard, as IMO they have already mentioned. You mentioned about the fuel standard. Same thing. We are working here for the vehicles. We try to increase the shift toward public transportation, and as well for the freight transport. Building on what the speakers in this topic they mentioned about different type of misconception in their field, I'll share some common misconception for the land transport sector, which is always revolve around the green mobility. It could be about lack of government policy support or governance, lack of infrastructure, also the environmental concerns. So to clear up all these misconceptions, I'll go over the details of our national UAE EV roadmap. What we do in 2022, we initiate a transformational project, a global market for electric vehicle, which was approved, where we aim to foster the adoption of EV and encourage the global market to open here in the country. To spread wide EV user in the country, and hoping to make UAE the leader among all the country for having increasing the share of sale for the EV from among the total number of vehicles. So if we move to the next slide. So here the slide shows the main milestones that we already achieved. First one is the National Electric Vehicle Policy. This policy aims to help us to standardize the infrastructure specification for EV charging station. We try to align with all the government, the local authority that are responsible for preparing the infrastructure for installing the EV charger. Also, we through this policy, we aim to increase the share of EV by 50% by 2050. This is help us to reduce the emissions by 404 kiloton of CO2. Therefore, what we try to do is having MOU partnership with the private sector. Our aim was just to open market for 5 companies. However, the ministry surpassed this target, and in the current stage, we are open market for 10 companies, where we help them to install their EV charging station and increase the share of the number of EV user in the country. So by 2023, 10% was increasing in the sales for EV, and now the percentage of the EV is 1.1%, and for the hybrid is 1.9% by the end of this year. Also, we have a national guideline for installing the electric vehicle charging station. This guideline help us to synchronize all the standard and specification for the EV charging station that will be placed on the highway and the rest area for the federal road in the country, and contribute to have like common standard and guideline for all entities and all the private sector who want to install the EV charger in the country. Another aspect that worth to be mentioned is the national platform for electric vehicle charging station. This platform serves as centralized hub when all the stakeholders locate their EV charging station. So we have a geographical distribution for all charging station, and we use AI as a tool, so we help us to forecast in the future the best place for installing additional EV charger, and it's become easier to all partners here in the country to set their strategical plan. On the other hand, we have as well for the all EV user and the community an application. This application helps them to locate different type of EV charger, and they can even book it. So it's show our commitment to help community and help them to adopt the green mobility. So this is like my posting that we are trying to help the country to move toward green mobility, because they say there's a lot of challenges, and we don't know if the country, if the community will go and help the ministry to achieve its goal of increasing the number of EV. Also, we prepared the infrastructure for to be ready for installing the EV charger, both for AC and DC and different type of chargers. So prior to our project, if we find that 44% was increasing in the number of electric charger. So it was before 455, and now we have 914 chargers. This help us to increase and growing the fleet of EV in the country. And we are trying as well, if we see for the government, they all try to increase the number of EV in their vehicle fleet. I'd like also to expand that by adding other project, which is establishing the EV service center. We are working to establish 3 EV service center. This center aim to help the EV user to get a tailored service for them. They will have their high-speed chargers and the maintenance for the EV and other services that will be there by partner with the private sector. Also, we have the EV GCC border where we install our fast EV charger. This shows that we are also committed to increase the adoption of EV, not in the country, also the region. So anyone from the neighborhood country like Saudi Arabia or Oman, they can find in the border the fast charging station. So it will be seamless movement between the country. And final math busting related to the environmental aspect regarding the EV is the battery life and recycling. Because it's a big challenge to recycle the EV batteries. So what we did is establishing the first facility to recycle EV battery in the region. With this, I conclude my presentation, and I hope that there is Like we cover every aspect of the transportation from aviation, maritime, and finally with the land transport. And thank you.
Thank you. Thank you, Meitan. Now I suggest the three of us take our seats and we'll have a brief question and answer session. I think, well, we certainly have 7 minutes until 4:30, but I'm told we can go over a little bit if we need to for questions, so we don't need to finish strictly at 4:30, although it has been a long day, so we'll keep it, we'll make sure it doesn't go on for too long. So thank you both for very stimulating and informative presentations, and now the floor is open to the audience for questions. Yeah.
I don't need the mic. For the recording. Oh, okay.
Thank you. Thank you very much. That was very interesting. I'm particularly interested in the transport sector. So I'm the UK Science and Innovation Lead at the British Embassy here. I'm not an expert though, but I'm familiar especially with aviation, just because I know lots of people working in the sector, including my husband. And I was curious on aviation, on the different initiatives that could be, or you know, different changes that could be made before having the hydrogen planes. What are your thoughts around the type of aircrafts that are being chosen by different airlines? You know how different have different strategies. Some airlines are going now for smaller aircrafts. I'm not sure if, I mean, there is a sustainable focus, but also I think is optimization, operational reasons. So I would like to get your thoughts about that. And then I have a question for the shipping industry, if that's okay. You've explained everything related to emissions. I wonder if there's any work being done around biodiversity loss, the impact in the marine environment. Yeah, those are my questions. Thank you.
Don't know if this is on. No, I think so. This one, I think. Yeah, it is this one. Great. Well, thanks for your two very good questions. I have to say, I'm not an expert on the mix of aircraft, so I'm stepping slightly outside my comfort zone. But I think we need a mix, and people are still talking about electric aircraft, of course, as well. There's a concern that with electric aircraft, at airports, this is a practical consideration at airports, that you need stands that can handle both a conventional aircraft and an electric aircraft, so dual-purpose stands. And there have been some studies on the concern that converting to dual-purpose stands will reduce the throughput of aircraft and with the rate at which aircraft can enter and leave. I mean, another concern for me with the aircraft of the future that hasn't really been explored is the certification envelopes in terms of gusts and turbulence. There's the certification envelopes currently use a gust model from the 1960s, atmospheric measurements made in the 1960s, which is out of date even today, but certainly in a few decades' time. Because of climate change, those gust statistics will be ramping up. So I think there's some work to do around strengthening airframes and ensuring that, I mean, I'm not suggesting planes are going to start falling out of the sky because of turbulence, but there's wear and tear and fatigue on the airframe, micro cracks that reduce the lifetime of the airframe. And the Boeings and the Airbuses of the world are aware of this and are taking appropriate actions in terms of thinking through the consequences. Because, of course, the aircraft that will be in the skies in the 2050s are today being designed. So we can't wait decades. We have to build those factors into our design specifications today, really. I'm not sure I've answered your question, but I've given you some thoughts anyway. I hope that's helpful.
I think, sorry, maybe it wasn't specific. You know how there are bigger aircrafts? Mm-hmm. At least here in the Middle East, they tend to use big aircrafts, and some airlines are thinking on changing towards buying smaller aircrafts. but with the contrails, that would mean like more flights just to satisfy all the different demands rather than doing the big 380s, Dreamliners. They are going, so there's a couple of big, huge demand for the new 321 Neo, I think. But then the contrails, that might mean more flights in smaller aircrafts. What's the impact of more flights in smaller aircrafts in comparison to the bigger aircrafts?
Yeah, it's an interesting point. Sure. Okay. I get that. So if you have a certain number of passengers to transport, you could put them all on one aircraft and get one contrail, or you could put them on 2 or more aircraft and get 2 or more contrails with
the bigger aircrafts at times they don't really work well with certain airports because the airports don't have the capacity to receive such a number of passengers at the same time.
That's correct. You need a long runway, for example. Yeah. So there's a tension there and a calculation to be done. But as I say, I think we have the knowledge today to deal with the contrail problem. There are startups that claim to have essentially solved it. So it might not be something that we need to worry about, in fact.
Thank you. Interesting point, because I think in shipping it's similar, and there's an end to, I think, to the economies of scale. If you look at the largest container vessels which are now operating and on order, they can actually carry up to 25,000 containers. And I think there are now some orders that go up to 27,000 containers. But there are fewer and fewer ports that can actually handle these kind of ships, and the associated infrastructure. So the length of the berths, the length of the quays, the depth. So you need more dredging in order to have access. There's more risks of accidents, like in the Suez Canal, where ships get blocked. So I think in aviation, that there's kind of an end to these economies of scales, and whether that has an impact on energy efficiency, I think it depends, because yes, on a large route you maybe win, but like in aviation, then you would have certain hubs and you would still have to carry or fly around or ship around the goods that come into hubs, into smaller ships to other ports. But coming back to your other question on biodiversity, we do actually do quite a bit of work on biodiversity as well. We have a number of treaty requirements that address biodiversity. One of them relates to invasive species in ballast water. I don't know how familiar you are with shipping, but ships carry a lot of what is called ballast water in their tanks, and that is needed to kind of optimize their drought, so how deep they are in the water, particularly when ships, for instance, from container ships coming from Asia, there is a trade deficit in Europe. So the ships come heavier loaded from Asia to Europe than when they go back. So they need to compensate that with ballast water. The ballast water is taken in a certain port, and then it's released at the other side of the world when they are loading again. And so this has led to actually carrying around species from one part of the world to the other part of the world, and then these species being released in waters where they don't belong, and that had impacts on local species. So we have a treaty that actually regulates that, and that sets quite strict requirements and filters on that water, that is the ballast water that is taken in one port and then being released in other parts of the world. We're working also on the water noise. So the noise of the ship engines, of the rotors, has quite a big impact on mammals in certain parts of the world. So we have just agreed on kind of looking into how to phase that out. And it's actually quite an interesting area, because there's a lot of gains that can be made with energy efficiency measures. So the more optimal the rotor of the ship becomes and the less energy it uses, it can also reduce quite a bit of noise. And then we have areas around the world that have been designated as special protection areas, so high interest special protection areas where shipping cannot go through. So they're routed around it in order to primarily to avoid collisions. So there's regular collisions between ships and whales, for instance. And so in those areas where this happens quite regularly, we have now imposed either shipping lane restrictions or special areas that have to be avoided altogether. So that's what we're doing from the shipping industry. But the UN actually agreed on a new treaty last year, which is the BBNJ. It stands for Biodiversity Beyond National Jurisdiction. And so this is a new treaty that has been negotiated for actually a decade or so. It still has to enter into force because countries need to ratify it. But it regulates the high seas, so where there's no exclusive economic zones, where there are no territorial waters, and so the area of the seas that is owned by nobody, and where there's an increase of interest in deep sea mining and other kind of activities in these areas beyond national jurisdiction. And so through the UN, there's now a new treaty that should try, or that aims to avoid all the kind of negative impacts, including on biodiversity, or particularly on biodiversity of these kind of activities in the areas beyond national jurisdiction.
Just a quick question, if I may. Paul, can I ask you, I was gobsmacked about the potential and the pathways you outlined for reductions and impact reduction from the aviation sector. That was a real mythbuster for me, because I wasn't aware that so much could be done in such a short time. So let me ask you, if you had the head of the regulatory body sitting in front of you right now, what single thing would you want them to implement right now? So that's one question. Ro, can I ask you about, again, I was actually quite struck about how far the industry and the sector or the regulator has come in looking at whole maritime and shipping and regulations. But the myth I have in my head certainly is that the vast majority of ships use the dirtiest bunker fuel. And is that what percentage is that currently? And am I right in to understand what you said, is that is going to go to zero? And Maita, can I ask you, what is the percentage of emissions related to transport or roads and motor car use currently in the UAE? And what is that percentage going to go down to, if I can say? And is there any prospect for I know this is a tricky subject over here, but price rises in fuels? Because that is a clear and easy way of reducing demand. You talked a lot about demand reduction, but I don't think, unless I missed it, you mentioned price rises or taxes on fuels for reducing demand. Thank you.
Thanks, Tarek. Good questions. I think for me, the immediate, obvious thing to do that is not being done, well, not quite sure why it's not being done, but it's this dispensing with this whole issue about air traffic control fees. Countries charging high fees to fly through their airspace. So there are countries in Europe, I won't name them, but who charge a lot, and the flight route will just fly, hundreds of miles around. Yes. I'll have a chat up when the recording stops. But and there's Eurocontrol, which is the European Organisation for Air Traffic Control, that they're trying to harmonise European airspace, which would immediately solve that problem. In the same way that North American airspace is certainly over the US is kind of harmonised. We need the same kind of approach in Europe, I think, to that. That's what I would do immediately overnight, because the savings are, for so little effort, at least in my head, so little effort, the savings are quite big.
So indeed the fuel used by ships is bunker fuel, heavy fuel oil, and it's still used by over 99% of the shipping fleet today. We have taken quite some initiatives to clean up the fuel. So in 2020, we imposed a global sulfur cap on the heavy fuel oil, and we reduced it actually by 50 times to 1%, or 0.1%, which is still 100 times higher than the maximum sulfur content in road petrol in Europe. But it was a massive decrease, and it actually led to some discussion about some of this cloud formation on the major shipping routes, which is quite interesting. But yes, still 99%. We do see, particularly the larger container lines, Maersk, CMA, CGM, Hapag-Lloyd, MSC, to a certain extent, investing in new builds, which are renewable fuel ready. So they have dual fuel engines. I was actually 2 months ago in Copenhagen for the launch of a new Maersk ship that is fueled by renewable methanol. They actually the ship came from a yard in Korea and sailed to Copenhagen, and on this maiden voyage it actually had to use biomethanol because it couldn't purchase completely renewable, let's say, wind or solar produced methanol around the world, because there's simply not enough supply for the shipping industry to access this fuel, and that is one of the big constraints. So we are working on carbon pricing, and that should then actually kind of bring down the price gap between heavy fuel oil and the renewable alternatives, which are 5-6 times more expensive than HFO, heavy fuel oil. And so that is really the challenge, to have an incentive, an economic incentive that brings down that gap.
For the first part of the question, we aim to reduce the emission for the transport sector in the country almost by a half by 2050. But the number of how much it's counting in the total emission here, I know the number, but it's not coming in my mind now. And for the second part of the question, what's will happening when rising the prices of fuel or having tax? I already noticed that many people now shifting from conventional vehicle to the EV because they face this challenge or face this problem. And if you notice that the electricity tariff here in the country is one of the lowest comparing to the other countries. So this as incentives to support them to move from conventional vehicles to the EV cars. Thank you.
Thank you. I wanted, of course, as an academic, to quibble over jargon. So what Paul said about real zero was actually, well, net zero, or one might say geological net zero, because you still have a large chunk of engineered carbon dioxide removal and storage in that. But I agree with you, it's not what most people mean by net zero, but in slight at risk of sounding slightly defensive, it's what we meant by net zero when we sort of started this conversation. And it's obviously what we need to get to. And it prompts the question actually to all of you, really, which is that is the obsession, I should probably use the word, well, never mind, I used the word once, with going fossil free in the COP process at the moment, actually driving us into some cul-de-sacs when it comes to these hard-to-abate sectors. For example, you were talking about e-methanol. It takes, I think, about 9 gigajoules per ton to actually capture carbon dioxide from the atmosphere, and I think it takes about 3 times that amount to turn that carbon dioxide into something useful like methanol, because carbon dioxide itself is such a low-energy form of carbon. So you could do much more good for the planet if you just captured 4 tons and made your shipping, therefore, or your flight carbon negative by just sticking carbon dioxide back underground and carrying on using fossil fuels, then you could, by virtuously going fossil free, you're actually much better for the planet. So what can we do and yet the entire industry and philanthropy and everybody is obsessed with synfuels, not geologically balanced fuels or whatever you want to call them, where we just get rid of the carbon dioxide rather than turning it into something else. What can we do about this? Because it's sort of, Institute of Physics should have a view on this, because it defies basic physics to do that to carbon dioxide.
Yeah, sure. Very good question, and we in the strategy that governments agreed on in July, they agreed on a net zero target, but they haven't actually defined what that means for obvious reasons, because they couldn't find a political agreement amongst the terminology. And I think your questions are spot on, and it's one of the issues that the shipping industry still has to deal with. And I would say energy efficiency measures is really, really, really one of the elements that we continue to look into, because of I showed it on the slide, you mentioned it, like the big amount of energy that can still be saved by applying all these energy efficiency measures. But it does seem that the world now doesn't want to really, also in the shipping industry, it's less sexy to talk about energy efficiency measures than talking about renewable hydrogen as a propulsion fuel for the shipping industry. So I think we'll come back again to that realization that what governments agreed upon is really going to be extremely difficult to achieve, because we'll have to, or the shipping industry will have to fight with other sectors to get access to these fuels. And yes, there may be other sectors or other parts of the economy where you can make much more savings in terms of the overall carbon emissions by using these fuels compared to the shipping industry. And that may mean that we will have to use carbon credits or any other kind of, mechanism for the shipping industry. Well, I see you, but it is the reality of the debate in COP, but also in IMO, that all these kind of buzzwords and what some industry groups are trying to put forward, what some civil society groups trying to advocate within the IMO, still need to find a place and some kind of a reality check, in my view, about what really makes sense for the shipping industry in order to kind of reduce its footprint. And I don't think we're quite there yet. We know that I mentioned like the Maersks of this world, they are quite advanced, but they have, particularly during COVID, they have made billions of profit. The main shipping companies, because of the huge increase in freight rates. And so they're kind of divesting and investing the money that they made into other parts of the maritime value chain, including direct investments in renewable fuel production companies in order to ensure access to these fuels. But whether this works for the entire industry, I don't know. No?
I can't speak for you.
Hi, so kind of two questions. One more for like the international kind of shipping aviation. I didn't actually realise that fell outside of the Paris Agreement. That was quite interesting for me to understand there. So does that mean that the emphasis is kind of less on, could government use this as a way to kind of make themselves net zero a bit easier? Or that's probably not the wrong way of saying it. Or is there less of an emphasis on shipping and aviation compared to what you see elsewhere? Because the governments kind of have less control if you have like a UK-owned vessel operating in another country.
Yeah, I think that's a good point. Yes, indeed. So Paris doesn't cover it, and so it's not domestic governments and legislation. It's these international UN sub-agencies, the IMO and ICAO, which is not to say that they have less teeth. It's just a different comes from a different place.
Okay.
Yeah. Do you have anything to add?
I can add a lot, but I'm not sure if you want to know. So basically, the difficulty in comes from calculating the emissions. And governments have been negotiating this for years, including here in COP. So we participate in the formal negotiations at COP, and we contribute and we report our work to COP. But it's a highly contentious issue, international aviation and shipping in a UNFCCC context. And that is because there's a huge disagreement amongst governments on how to calculate and account the emissions of international shipping and international aviation. So there's some that advocate that the emissions associated with the sales of either kerosene or bunker fuels for the shipping industry should be added to the emission inventories of the countries where they're being sold. But as you can imagine, there are some countries which have large bunkering hubs, including my own, the Netherlands. The Port of Rotterdam is a huge bunkering ship fuel hub, Singapore, the UAE. And they advocate, well, we sell these fuels, but the fuels are not burned in our territory. So why do we need to be solely responsible for adding the emissions associated with the bunker fuel sold to our inventories? There are others that say, well, the flag of the ship should be responsible. But then again, the most of the ships are actually flagged in developing states, like the Marshall Islands, which is the second biggest ship register in the world, which is a small island developing state, which is actually on the verge of disappearing. The other alternative is adding it to the inventories of the ship register, so where the owner, the actual financial ownership is. Anyway, it's a mess, and governments cannot agree on it, and so it's ICAO for aviation and IMO for shipping that are the responsible authorities to do that in order to avoid carbon leakage, because in that way you have rules that apply for every ship regardless of their flag, regardless of where they operate, and so the emissions are eventually accounted for through our rules, but they're not allocated to an individual country.
Okay, thank you. And one question is more kind of locally now. So there's a lot of investments in the Gulf now for hydrogen. We've heard about some thoughts on hydrogen earlier. I noticed the strategy seems to be more on charging stations, EV, recycling batteries. Is there any kind of scope between now and 2050 for exploration to hydrogen vehicles and hydrogen fueling?
Yes, there is, but for our ministry, like if we are talking about the National Demand Side Management Program, we are focusing now on EV. There are some strategies or some program they are trying to adopt the hydrogen cars, and we see there are some hydrogen cars. The Ministry of Climate Change are negotiating this. And they there is a possibility to have it, and maybe to add this also under our mandate in the National Demand Side Management Program. Thank you.
Okay, thank you very much, Paul. Thank you very much, panel. That's been terrific. I think it's time for us to wind up. Thank you very much. So, folks, we're at the end of the fascinating day. Honestly, my mind is buzzing because there's been a lot to digest. And I was thinking, sitting there, how do I pull this all together into some sort of coherent summary? And it's beyond me. I need time to digest it. I think there are certain themes that have come through. We heard about capital and flows early on. We heard about different technologies. We heard about resilient cities and the need for planning and organization and the role of physics in all of that. We've heard about some of the challenges, nomenclature more recently, and terms, but the position of where we are in terms of climate science. We've heard about the global energy mix, a lot of discussion around CCS. In fact, that if there's one thing that's run through, I suppose, through today is the discussion around carbon abatement, the use of fossil fuels, the potential blind alleys we can take ourselves down, the various vested interests that are there, and also the time frames about actually how little time we've got to really get those emissions down before we get into the uncharted territories that we heard about again for miles. I think the last panel was very, very interesting in terms of transport. I certainly was not aware about the potential major progress in aviation and also in the maritime sector. So thank you for all. I'm just going to, because I just want to thank all of the speakers. I'm going to name check everybody. Charlie Ogilvie for excellent chairing of the first session and actually challenging us about the role of public perception and the role of public opinion in motivating political discourse and political decision-making and political leadership. Sri Rajesh Veeragavan for a fascinating insight into what's going on in India in the nuclear power sector and the potential pathways in modular reactors and the discussions that are going on there. Lords Vega around CCS and hydrogen. Professor Nana Klutse about, well, expertly chairing that panel on societies and cities and actually bringing it together in terms of resilience with different viewpoints, because we had an investor, we had a management consultant, we had Hassan Shafi, we had the investor Abu Chowdhury, all thinking about it from different points of view, but actually it all sort of fed back into a closed loop of understanding about resilience and pathways to options, district cooling. And then finally, Professor Paul Williams, again, fascinating discussion around sustainable transport systems, a major part of our global emissions. Some of them are hard to abate. We know about hydrogen, not a silver bullet for everything, but potentially in terms of transport fuel for those very heavy vehicles, maybe ships, but maybe not. It may actually be better to capture the CO2 again. We had Roel telling us all about shipping and the maritime sector and the huge advances since I last looked at it, which was really encouraging. And Meta bringing it all back to where we are today and with COP going all around us to hear what's happening in the home country in terms of transport systems and the policies and the demand reduction you're putting in, which is really fascinating. So, to one and all, I know I said Miles. I didn't have my notes, so I didn't name check Miles. I beg your pardon. How could I possibly forget Professor Miles Allen, FRS, distinguished climate scientist at Oxford University, and Anne Crean, who actually did a fabulous job of talking through the key highlights of our new report. And I'm going to mention this for one last time: Physics Powering the Green Economy. You can download it from the website and from the QR code. It's actually a terrific read, but with some really great insights as well. So on that note, I'm going to final thank you to Elora for keeping us on track and doing all the fixing and the organising to getting us here, and to Dom, who's underpinned all of this from the Institute of Physics. And final thank to Institute of Physics for this event. Thank you very much.